Good morning everyone, it's day 24 of Advent of Code. Anagon Live is back online and we are preparing to get started. We don't have a lot of time left because it is already less than 1 minute to 6, or almost 1 minute to 6, and that means that our puzzle is going to be released. So it's quite exciting. It's the last day tomorrow and today is the day before, so we have only 2 puzzles left and I haven't solved all of them. I will still try to do that. So I'm not sure about day 25. It might be a little bit easier than other puzzles because it's Christmas after all, but this is really the last puzzle that still might pose a big challenge. Yesterday was alright, so we'll see. It's probably not going to be related to int code, as we all expect int codes to happen on odd days. So yeah, we'll have to see. I did have a good long sleep today, so I hope I'm going to be a little bit more focused than in some of the other days. I'm really struggling sometimes to have a sharp brain. Hey G, good morning. Good luck to you too, and see you after the puzzle. Day 24, Planet of Discord. You land on Ares, your last stop before reaching Santa. We're almost reaching Santa. As soon as you do, your sensors start picking up strange life forms moving around. Ares is infested with bugs. With an over 24-hour round trip for messages between you and Earth, you'll have to deal with this problem on your own. Ares isn't a very large place. A scan of the entire area fits into a 5x5 grid, your input. The scan shows bugs and empty spaces. Let's have a look. Okay, that is very small indeed. Let's save it in day 24. Oh, I've already saved that. How is that possible? Oh yeah, that directory is pre-made. Okay. So where were we? Each minute the bugs live and die based on the number of bugs in the 4 adjacent tile. So this sounds like an Conway's Game of Life puzzle. A bug dies unless there's exactly 1 bug adjacent to it. An empty space becomes infested with a bug if exactly 1 or 2 bugs are adjacent to it. Otherwise, a bug or empty space remains the same. So I'm going to skip quite a bit, as this is just Conway's Game of Life. Watch for the first time a layout of bugs and empty space matches any previous input in layout. Okay, so when we have a cycle basically. To calculate the biodiversity rating for this layout, consider each tile left to right from the top in the top row, then left to right in the second row, and so on. Each of these tiles is worth biodiversity points equal to increasing powers of 2. Add up the biodiversity points for tiles with bugs. In this example, okay. What is the biodiversity rating for the first layout that appears twice? Alright, let's try that out. So we need to parse our input. Well, maybe we can do it a bit faster this time and not parse input. Let's just copy the whole thing, because it's not that big anyway. So grid is triple string like this, and let's strip it from white spaces, and then we'll have our rules. So we have a while loop that goes forever, and a bug dies unless there is exactly 1 bug adjacent to it. Okay, maybe we'll do 1 iteration first. For y in range 0 till length of the grid, maybe we should calculate the width and the height first separately. So grid, let's split it also on new lines. So the length of the first item is the width and the height is just the length of the grid. And for X in range 0 till height, I hear that the music has stopped for a moment. And it looks like my internet connection has dropped. I hope it will restore very soon. It might be related to the fact that I have just upgraded my connection. I need a bit of more upload, and I think they might have just reset my router just in the middle of the stream. So I'm sorry for that, but I will upload this video later. So in the meantime, I will just continue. And let me see what I will do about the music. I guess I'll add the music later. So we'll keep going. So we're looping over the width and the height, and then we need to calculate the new grid. That will be also a copy of the other one. And the new grid's position, let's say that we evaluate all positions around every bug. And let's see if we need to consider diagonal neighbors or only adjacent tiles. Okay, adjacent tiles. So the neighbors are here. The neighbors is a list of tuples with relative positions. So we have -1 and +1, oops, on the x-axis, and on the y-axis we have -1 and +1 also. So we'll go over all of the neighbors. And then, you know what, actually I am going to play some music. I'm so used to it now that it feels very odd not to have any music in the background. Luckily I downloaded the music yesterday, but that means I can just play it locally from my computer. Let's see, I have it right here. Alright, there we go. The good old familiar Christmas music is now back. Just when the internet is restored, so we are back online, luckily, and we might have a better upload speed now as well, and that is working. So as you can see, our upload speed is now 6 megabytes and it was 3.5, so that is a nice improvement there. Just unfortunate that the stream got interrupted right now when I was online. So I just made a double loop and we're iterating over all of the neighbors. And let's see the neighbor state. Let's count the number of bugs around us. Bug count is, maybe we can just do a comprehension. The neighbor for neighbor in neighbors. If let's see, we need to add to that the x and the y. So that's dx and dy. Hey G, yeah, I'm back online. I was disconnected because my provider just upgraded my internet connection. You know what, I'm gonna do it in a loop anyway, just to be a bit quick. So we're going to add bug count if, and only if, the neighbor position, which is nx and ny, which is y plus dx and oops, x plus dx and y plus dy, if that is within the range. So if it's in the range of the width, I noticed that I swapped the height and the width here. range 0 till width, and y is in the range of 0 till height. Then we're gonna add a bug if there's actually a bug there. So and y and x, if that equals a hash, then we have a bug. Okay, what else? The x apparently didn't work. I have to do it like this. Now we're counting the bugs, and if the bug count is 1 and we are a bug also, so tile is t, y and x. So if we are a bug and the bug count is 1, then the new grid position at the same location will be a dot. Otherwise, oh, and an empty space becomes infested if exactly 1 or 2 bugs are adjacent to it. So if we have an empty space and the bug count is exactly 1 or 2, so we can do it like this, in 1 or 2, then the new grid becomes a bug. And we are going to print it. Let's join all of the lines in the grid with new lines. And after iterating over all of the positions, we should of course assign our new grid to the grid. And let's print it once before and then once after an iteration. So here there's something not going right. We cannot replace a string like this the way I'm doing it now, but maybe we can, let's see, split the grid up into lines and characters. So line for line in grid, but the line should be split by nothing, like this. Empty separator, okay, maybe no separator then? No. Maybe we can do, okay, for every line in the grid we want to return the character. How does that work? C for C in line, for line in grid, like this? Or maybe the other way around, like this? Not sure if we get the right grid though. Ah, now we get a one-dimensional list actually instead of lines with characters. So we want a line with something like this. Hold on, how does that work? Okay, so our grid is a comprehension with a C for every C in the line, for every line in the grid, like this, right? And we still get something that is not working. Ah, yeah. So our join function now should go a little bit differently. For line in grid, print concatenate that all together, like this. That is our print function. Print grid. And at the end we'll also print the grid. So it looks like we didn't actually change anything. Let's look at our input. So we start with a hash in the top of the middle. So maybe we should print the grid actually. Okay, that works. And then in the end I want to print an extra line so that we can see where they start and end. Okay, and now we just need to know when do we get a repetition? And how can we know that? We need to keep a list of all the states that we've had so far. So I'll keep a set of that. And the set will be, what will it contain? Maybe maybe we can actually concatenate everything into a string and keep that as our kind of value. So basically, if print grid would return a string, or maybe let's say a grid as string, then we'll just we'll receive a grid as an input, G, for line in G, for C in line, and then we'll have a string maybe, or maybe we'll just return a list comprehension. So we'll join by new line all of the lines, and what we'll join is actually a list comprehension again. This. So we'll join all the characters in the line, and then we'll join all of those. Wait a second. I think it should be like this. Yeah, grid as string. Okay. And then we have our states, and we're going to add to that the grid. Let's see if that actually runs. Unhashable type list. Okay. And where does that happen? When we add it, because we have to do a grid as string with the grid. Okay. Alright, that's it. Now we can keep running this until we are done. And then we have to calculate, of course, the biodiversity metric. So if our grid as string, which we're going to keep here, if our grid as string is already in the states, then we are going to break, and otherwise we're going to add it, maybe like this, and we're going to print biodiversity of the grid. And to do that we need to count a power value for each of the positions where there is a bug. Okay. So for, maybe I can just calculate the biodiversity here. So let's start with 0. And if we're having a bug like here, oh, and what happens if we don't change anything? What happens then? What happens if none of these rules apply? Otherwise the bug or empty space remains the same. So we do have to have an else statement in the end. So the new grid y and x will become whatever it was. So that means that if we want to count here, we have to count it very smartly. The biodiversity is now 0, but we cannot add only in this case, because sometimes we might already have a bug and then we also want to count it. So you know what? I'll just count it in a separate loop to make it a bit cleaner. So the biodiversity is 0 for x and y, double loop again. If the grid at y and x equals a bug, then we're going to add to the biodiversity a power of, what was it? 2 to the power of the position, right? That is y times the width plus x. Just like that. And then we'll print the biodiversity. Okay. And we want to print it every time we do an iteration. Okay, that looks like a repetition. At least visually it looks like that. It is the same all the time. Am I still adding? Yeah, I am adding here. Okay, so what is going on? We get a lot of output. And we get a repetition quite soon, actually. I think this is the place where we have a stable state. And why is it not detecting that we have the state already? Maybe it's because I'm using strings and I'm not supposed to use strings for that. maybe we can just use booleans instead. So let's say that our grid contains true if we have a character, true if we have a bug, and otherwise false. Or basically I can just return whether or not we have a bug. So if it is true, and this is about getting the neighbors, and if we have a bug, renaming it to bug, and otherwise if we don't have a bug, then we're going to make it a bug, and here not. So I wanna kind of see if I can convert this into, if I can convert the state into some tuple. So the state is going to be a tuple of a tuple for every line. That will be another tuple. Let's print it and see if that looks correct. I know printing doesn't work anymore because now we're not working with strings. Messing around here a little bit. So we're going to try to join all of the characters in the line. But they are no longer characters, they are now strings. So like this, and otherwise a dot. Okay, and the grid as string also doesn't work anymore. So we need to join or see in line. How do we get it as a string? Actually, we don't get it as a string because we don't want that anymore. Okay, name G is not defined. That is happening here. For a tuple in grid, actually. Okay, now we get something that we can actually store as a state, but we still don't recognize it. Or maybe we do, and breaking is just not the way to do it. This is our only outer loop. So if we are breaking, that should actually work. Let's check the debug mode and see if we can detect whether or not this tuple is in our states. So our states is now empty, I think. Yes. And then on the next iteration, we have still nothing. Okay. And then when we keep going, oh, maybe I'm resetting states every time. Yes, I am. Okay. Well, that was easy to solve. So now we found it, and the biodiversity is counted as 0, which is wrong. So we need to work with booleans instead of strings. Now we should get something. And that is not the right answer, actually. Okay. Why is that? Bad. Probably related to how I am counting the biodiversity. Each tile is worth points increasing powers of 2, 1, 2, 4, and so on. Add up the biodiversity points for tiles with bugs. In this example, the 16th tile and the 22nd tile have bugs. So the biodiversity rating is like this. For the first layout that appears twice. Okay, so in our code, do we see that we get the first layout that appears twice? So that looks like 2 on the top, middle, and down. And here we have another one. So we didn't actually print it yet. I don't need to print the state. I believe that that would work. In the end, we print the grid. So let's print it before we actually exit. So now we get 2 states that look correct. And how do we calculate the powers? I need to use debug mode. So here we are. For position, I think I just skipped the first iteration. So for the first position, that is y equals 0 and x equals 0, then we should get an index of 0. The diversity should be 1. Yes, 2 to the power of 0 is 1. And so I think that that is probably going to work well. For the second row, we'll get 1 times the width, and the width is actually, well, 5, I think, in this case, plus x. So the first item on the second row will get index 5. So that should also work. And maybe our rule logic is incorrect. So we have an example. This is the initial state as an example. Let's play with that. So what happens if we run that one? The second state looks a bit different in the example than in my case, so there is a problem. And I will split it also on new lines. So a bug dies when there is a bug and there is exactly one bug adjacent to it, then we make it false, and otherwise an empty space if there's not a bug and the bug count is exactly 1 or 2 bugs, then we'll make it true, and otherwise we'll keep it as it is. Count the missing tile counts as empty space. This happens everywhere simultaneously, yes. That is what I'm doing by keeping a separate grid. Okay, so let's debug and check the first position. That should become alive, and in my case it is becoming alive. And maybe I have flipped coordinates by accident or something. I'm going top to bottom and left to right, yes. And my width and height look correct also. I don't think I've flipped any coordinates, so there's something else going on. So here we check all of the neighbors and oh, I see that oh yeah, this is only to count the bugs, right? So if we have something at nx and y, then we're counting it as a bug. So let's start at the first position. In the first position we found one bug to be around us, and on the right you can see that that is correct. And we have a bug count of 1 and we are in an empty space, so we should go to the next part. And we should say that it is true, and that is correct. And then we'll keep going. Then we'll have the second empty space, which is a dot. And there are no bugs around it, so it should stay empty. So bug count is tested. And we go to check nx, which is 0, and ny is 0 also. And here we say that we found a bug actually. 0, 0. That is strange. What is this value going to evaluate to? It says true. And that is why exactly? Why is 0, 0 true? And y and nx. So those are the first two positions, the first values. That should be here, and there's no bug there. But maybe our grid is messed up now somehow. I think I'm already in my second iteration or something. So let's break after. I think I need to have a little bit of coffee. Okay, so we haven't done our first iteration yet, and now we're counting one bug for the top left corner, and now we're going over to the next position on the grid, which is y equals 0 and x equals 1. We're gonna count bugs again, and we'll start by going up. And if we go up, that means, no, we're going to the left actually, and that means that it's out of the range of the screen, so we're going to skip it. But here we say that we don't skip it. Ah yeah, because going to the left on the second tile is actually still within the grid. And then we'll check what is on our grid. And for some reason I see now that we have booleans. I think the reason is that I am copying my grid in the wrong way or something, so that if I am changing something in my new grid, that we actually don't get a real copy. So let's copy all of the lines in the grid separately. So line and a slice for all the lines in the grid. Now we should get a copy. Yeah, we get a very different outcome. And I'm assuming that this is going to be right. And it's also not right. Oh, wow. Surprised that this puzzle gives me so much trouble. Let's return. Oh yeah, obviously I'm not running it on the real input, I'm running it on the example. Oh, and this answer is the same. No, it's different from what we had before. So now probably I'm going to have to wait. Yeah, I have to wait 35 seconds. Okay, we can do that. In the meantime, let me run it again on the example. Like, come on. Like this, and do we get the same kind of iterations? This is after 1 minute. That looks actually wrong. It doesn't look like we've implemented it correctly still. Okay, then debugging again. So the second pixel is going to have 0 neighbors, hopefully. So what does our grid look like now? It has only one value on the right, okay? So, do we have something? No, we don't. Okay, so if we run it till the end, then we get a bug count of 0. And that means that we should keep 0. Because that is just the case for which we don't have any specific rule. And for the second item, we see also a bug count of 0, so that will stay 0, I think. Let's see which conclusion we go to. That is keeping it as it was, yes. For the second one, we count 2 bugs. For the next one, we count 2 bugs, yes. So that will become a bug also. And let's see if that works. Yeah, it becomes true. And then for the next iteration, we count 0 bugs. That is the one in the top right corner. And do we count the tile itself or not? That is actually a good question. The bugs live and die on the number of bugs in the 4 adjacent tiles. Okay. So we count no bugs around this one in particular, and that means that it's going to be false, right? Oh, why do we... Wait. No, a bug dies only... Oh, unless there's exactly one bug adjacent to it. Unless... Oh, that is confusing. So, unless means always, except when, or when not. So when not exactly one bug, then it is false. Oh, that is so confusing. I think it just means that it's the opposite, right? No? Okay, I'm going to do some kind of stupid linguistic transformation here. So a bug lives only when there's exactly one bug adjacent to it. So like this. And then the other one, an empty space becomes infested. Okay, I guess that is correct. But how do we get false ever? Oh yeah, we get false when... Ah, I get it. So if the bug count is... No. A bug dies unless there is exactly one bug adjacent to it. So if we have a bug and the bug count is not 1, then we die. That is the actual reason. Rule. Like this. Okay, let's have a look now at the output. Yeah, that looks better. But for the second iteration, doesn't seem to go well. So the first iteration is correct, but then the second iteration is not correct. How can that happen? Oi oi oi. Unless there is exactly one bug adjacent to it. So if there's a bug and the bug count is not exactly 1, then we'll die, right? That's it. Seems kind of correct now. And the other says an empty space, so if we don't have a bug, becomes infested with a bug if exactly 1 or 2 bugs are adjacent to it. So the bug count is in 1 or 2, then it becomes true, and otherwise nothing happens. Okay. Wow. If you happen to see where I'm making a mistake, do let me know. I think conceptually this problem is not that complicated, but just the implementation where I'm messing up a bit. Oh, actually I should have looked at what was happening. So we know that the first line or so works well. So let's keep going until we have y equals 1. Almost. Now we have y equals 1. Okay? And we should get the conclusion that we get trues everywhere. Or keep it as it is, yes. For the next one we get true. That is the one here. Then another times true, yes. And another times true. Or keep it as it was, that's fine. Then the next state is also going to be true. Yes, and then finally we get a false. Yeah. Then the third row should be true a few times. Again, true. And then we get false, and that is incorrect. For x equals 3 on the third row, oh, actually that is correct, that is this row here. But that is also fine. Then for x is 4, that's the last one on this third row, we get to keep what it was. Okay, that also works. Now for y is 3, that is this row here. We are starting all the way on the left, and we decide that there should become a bug. Yes, here again a bug, and then no bug, please. Yes, no bug. Then again a bug, and again a bug, and then no bug on the next row, and then a bug and one more bug, and then twice no bugs. Yes. Okay, so that is the entire first iteration, and we get the right output. And now, oh, I know why. When I copy my old grid to the, when I copy my new grid to the old grid, I am using a reference by accident. So I need to do this thing again, where I copy every line as a new slice. That is a bit annoying. So now we get the right output. Oi. Wait a second. Yes, okay, that's actually right. Okay, now let's run it on the input. Yeah. Can we get some biodiversity? Yeah, okay. So, copying grids, that is the kind of lesson for today. When you copy grids, always make sure that you're actually copying it deeply. Thank you, G. Now, let's commit. Well, I have a lot of uncommitted files. Let me commit just this one. Commit. Day 24 already. The day before Christmas. Oh, okay, so I think that committing was good for this case. After careful analysis, one thing is certain: you have no idea where all these bugs are coming from. Then you remember Eris is an old Plutonian settlement, with recursive mazes? Clearly the bugs are coming from recursively folded space. The grid, this 5x5 grid, is only one level in an infinite number of recursion levels. The tile in the middle of the grid is actually another 5x5 grid. Ah, Alex has solved part 2 also. Nice, so I see that Hans, Fuzzy and G have also part 1. Okay, good luck on part 2, everyone. Okay, so it's recursive. And your scan is contained as the middle tile of a larger 5x5 grid, and so on. 2 levels of grids look like this, yes. To save space, some of the tiles are not drawn to scale, okay. Remember, this is only a small part of the infinitely recursive grid. There is a 5x5 grid that also contains this diagram, and so on. Also, the question mark in the diagram contains another 5x5 grid, which itself... Okay, I get it. It goes on forever. The scan you took shows where the bugs are on a single level of the structure. The middle tile of your scan is empty to accommodate the recursive grids within it. Initially, no other levels contain bugs. Tiles still count as adjacent if they are directly up, down, left, or right of a given tile. Now I want to know, when do you consider that a tile has a bug? When it's more than half or something? So, tile 19 has 4 adjacent tiles, yes, sure. How do you count? Oh, tile 14 has 8 adjacent tiles. Oh no. Oh, what? 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah. No. That's going to be very complicated. The rules about bugs living and dying are the same as before. Okay. Center tile is drawn as a question mark. Let's call this level 0. The grid within this level is level 1. And the grid that contains this one is level -1. Okay. Call. Okay, so as we go outside, so to say we go a level up, right? Center tile is drawn as question mark to indicate the next recursive grid. Call this level 0. Call this level 0. The grid within this level is level 1. So as we go in, the levels go up actually, up meaning they increment. Right. Okay, I'll assume that this works. After 10 minutes, a total of 99 bugs are present. Starting with your scan, how many bugs are present after 200 minutes? Okay. So we're going to have to keep a lot of levels. Especially copying now is going to be extra important. Yeah, so we have grids. And we have an infinite number of grids actually. So let's make a dictionary, a default dict, that will return a new grid every time we ask for one. That is lambda with a grid that returns let's say, false for all of the characters in the original grid. Or, well, I could also use the width and the height, of course. I'm not sure what would work better. So we're not using the C, yes. Huh? It wants me to remove the entire statement. That is a bit weird. Maybe like this. Okay. So that is our default dictionary. And maybe we can use the same trick actually for first part, so that I don't have to copy things anymore. So our new grid is basically... no, I cannot use this function. Maybe I'll make a function that gives us a new grid. Like extract to method. New grid. Yeah, that's nice. So every time we loop, we just want to make a new grid. Like at the start. Maybe like that. And then we can copy the grid. Let's also copy the grid with a function. Although when we do make a new grid for every iteration, we don't have to copy it anymore. That is an advantage. So we could do it like this. And I want to see if that still gives us the same answer. 213. 213. Okay. So just a short refactoring to improve our handling. And this is going to be part 1. And Arcanian has solved the second part of the puzzle also. And Valerie has solved the first part, so we're all going very well. Let's go over to part 2. Yeah, I'm going to keep this grids thing in the part 2 section. And let's run it. And the first item on our grid, which is level 0, that is going to be our original grid. And do I still need to copy it? I'm not sure. No, I guess I don't need to copy it. And how do we iterate? We iterate over all of the grids at the same time, I think. So maybe we can do like grids and new grids like this. And well, how many levels are we going to analyze? We start with all empty grids, right? Trying to find information about this. I think we start with only our own level. And when we print a grid, I want to make sure that I'm printing a question mark, I suppose. Maybe I'll call it print level. And then let's print by actually going over the dimensions. For y, I think if you do range with just a single integer, you iterate over 0 till the end of the range, right? So I usually do 0 till h, but maybe you don't need that. Range 10. Yeah, okay. It's a bit simpler to write. And then we're going to print a hash if the grid or level that we're going to print at y and x is true. Otherwise we'll print a dot. But if x and y equals a very specific position, that is the middle, which is 2 and 2, then we'll print question mark with no line ending, and we'll print a line after every row. So let's see if that works. Print level, grids 0. This is not valid syntax. Okay. Maybe this? Yeah, okay, so the printing works. Maybe we should print also which level it is. Depth. I'll do it the same as in the example. Oh, if we do a depth, actually then we don't have to specify the grid, because we can just say that L is all of the grids with the depth as an argument. But for that we do have to define them globally, unless of course I move this to my second part. So we'll print level 0. Yeah, that works. This one I'll just get out of the way. Okay. Okay. How do we start? Do we say anything about start? No. So this 5x5 grid is only one level, yes. Okay. 2 levels of the grid look like this, yes. Okay. Well, I think it's not that complicated. Actually, all we need to do is to have a different neighbor function. So maybe I can just copy this and let's see how we do it. So we go over all of the neighbors. Basically it's the same actually. And how about the biodiversity? We just need to count the number of bugs everywhere. Okay? So it's mostly the same, except that the neighbors are different. So neighbors was first defined as a 2D grid, but now it's going to be a 3D grid. And that will be like this. And why is this marked red? Unresolved reference grid. Did I just remove anything? No, grid is still here. Maybe I should make it global. This is part 1. Global grid. That works. Okay, so our neighbors. On the same level we have basically these guys. So maybe I'll prefix it with the current level. Or maybe I'll do it like this. Okay, that's just going to be a bit of manual editing with my small arrow keys on my Mac laptop. So this is all for the level 0 and for level 1. So relative to level 1, which means one level above us. In the example that looks like here. So one level above us is basically the thing in the middle, right? So that is basically looking at tile 14, for example. But I now realize that the number or the neighbors is different for each tile. Okay, so that is actually not that simple. So the number of neighbors is different for each tile. And I'm not sure if we have to specify where those neighbors are coming from. Yes, we do. Okay. So it's going to be a dictionary with all 25 positions. Wow. Okay, so that is going to look like this, and then each position will have a list of neighbors that have X, Y, and Z values. So I'll do it like this to make it a bit more clear that the first one is the level and the second one is the X and Y coordinate. So let's copy this 25 times. 2, 3, 4, 5. And copy this 5 times also. 1. So now we have 2, 3, 4, 5. And if I figure out a faster way to do this, then I will make it like more generic, but for now I'm just gonna do it like this. So we'll start by looking at, oh, maybe what I can do is make a little loop. Yes, you know what, I'm going to open my console and I'm going to make a loop that goes over y in range 5 or x in range 5. And then I'm going to return xy as a dictionary like this, and that will return a list with a tuple, some tuples in it, like 0 and 0, 0. Now we get this, and this is actually something I can copy back into my code. So that saves a little bit of editing. Nice, I like that. And but now, of course, all of the positions. Wow, that's going to be a lot of hassling. So here are all of the keys. Let's make a new line before each of them. Oh, the top row is here, second row, third row, fourth row, and the last row. Okay, so the first item is this one on the top left. It has two neighbors on the same level. So that is level 0 relative to it. And it has neighbors one to the right and one. I know what I'm gonna do. I'm gonna make aliases for all of the directions. So we have right equals this, left equals -1, up equals 0, -1, and down equals 0, 1. So that is a little bit easier to read. So it has one on the right. Maybe the structure would actually be easier to specify it for all of the levels. So basically it would look like this. So for the same level we'll have basically down and right. Yeah, I like that structure much better. So we'll have a dictionary with each level, some neighbors, maybe as a list instead of a tuple. So we have the neighbor down and right. For the level above it, we'll have up and left. And that is going to be similar to this one here. Yeah, okay, there's not much specialty going on there. For the second tile, we have left, down, and right. And for one level up, we have, that would be this tile, we have just up. And I think it is the same for 2 and 3 actually. For 3 and 4 actually. Yeah, because C and D also have just one tile above them from the other level. And then tile 4 should be the opposite of the tile on the top left, so it is down and left. And on the level above it, it has only up and right. Right, that should be this tile. And if you look at it from the inner perspective, you have up and right from another level. Okay. So this is the same as the bottom, except that we have to reverse up and down everywhere. So I'll replace up by X so that I can replace down by up. And then I'll replace X again by down. Okay, that is reversed. And now we have only the second row. Second row, like this 6 over here, has on the same level a neighbor on the right and down of it, and on the level above it, that would look like here. Here should be a comma. There it has a neighbor on the left from the higher level. That's it. Oh, wait a second. F also has a neighbor on above it, yeah, like this. Because all of them should have 4 neighbors no matter what. And F is going to be the same as the one on the right, except that left and right are reversed. And then we have the second tile from the second row, which has neighbors on all 4 directions, up, down, left and right, and nothing on another level. And that is the same for the second tile from the right. And the middle tile on the second row has... Oh, wait a second. Did I just copy the whole line? Oh, yes, I did. Oops. I think I did that earlier as well. Uh-oh. It should be 1, 2, 3, 4. And here 1, 2, 3, 4, but with y coordinate 4 instead. Okay, that is a bit dangerous. So 0, 1, 2, 3, 4, and on the left we should have 0 till 4 every time. Yes. Yeah. So we're looking at the second tile in the middle tile on the second row, and it has up, left and right on the same level, and on the level above it it has nothing. Actually, we should look at the level below it. That is going to be down. So I made a mistake. I didn't consider... I always wrote one level up rather than up or down. Wait a second. On some cases we are calling it depth instead of level, but levels go up and depths go down. So how can we look at it? In the example we have each level. Okay, so I'm assuming that this is the outer level here, and then we're going more in and in, right? Okay, so the outer level, I've used -1 for that so far. And yeah, depth equals level, which doesn't make sense, right? Because in a building, your floors are going to go up. If this is your building, and then your depth is going to be like this. But that would be depth too. But not in this puzzle. Okay, thanks for that. So we are looking at the second tile from the middle tile from the second row. That is this one. It has up, left and right, and yeah, and then the inner tile which goes up, that has down. Okay, and now we are looking at the middle row. So on the left side of the middle row we have one up and one down and one right, and on the outer layer we have only the other one that is remaining, namely L, and the opposite happens on the other side, like this. And then the second tile from the left in the middle row has up, left and down, and on the layer that is going up has only one, which is right, and that is the same for this one, up but then mirrored, like this. And the middle tile has no neighbors, I think. The middle tile we don't even consider, right? It has no neighbors. No middle, no neighbors. Okay. Oh, that was not it. We were almost done. We still have to copy this part. Yeah. And this is on the bottom side of the middle. So that means that all of our up and downs should be flipped. So I'll replace down with X, up with down, and then X with up. If you want to know how I do that, please look at my shortcuts also. I'm using add selection for next occurrence, and that is how I add a lot of cursors. And I'm doing minus, I'm using shift to reverse it. And I think I've made my own shortcut for that. It's very handy and I use it a lot. Okay, those are all the neighbors, and now we need to actually implement our algorithm. So the bug count is using the neighbors for that particular tile. That is X and Y. And the neighbors now also contain a delta for the depth. So I'll call it DD. And Arcanian has solved part 2 also. Good job. And bug count starts with 0 and we're checking all of the neighbors. But we need to look at grids and look at the new delta or the new depth. And the new depth is the old depth that we were looking at. Depth plus delta delta, or DD, delta depth. And we haven't specified the depth yet. So let's do that now. For D in range. Ooh. That is going to be all of our grids that we have found so far. So like this, for D in grids. So here we're counting. And what else? So we need to say that the grid for our current layer is updated. So nGrid is a new grid. And then we're going to have to replace it in our layers. So our grids at layer D is going to become our new grid, our nGrid. Okay, that is at the end of each. Let's see where I need to stop. Yeah, okay, so at the end of iterating a single layer. Wow, look at the leaderboard, by the way, and look at all of those stars. It's almost completely filled up. I'm very happy to see that we've made it so far. 25 stars is what we're going to see. Okay, maybe should we print it or not? I'm not sure. We're tracking states, but that's no longer necessary. We don't need to track biodiversity. We might want to keep the number of bugs in every grid. No, I'm not sure. We do need to repeat 200 times exactly though. And when we're done, we're going to count all the bugs. So for D in grids, for Y in range H, for the height, and for X in range X, let's count the total number of bugs. The total bugs is +1 if we have at that particular grid, at that particular position, a bug. Otherwise, we'll not add it. And that is the total number. Let's run it. I don't know if this should work. Cannot unpack non-iterable int object. Okay. Our neighbors list should contain a tuple with a tuple in it. Oh no, not anymore. I just have a list of tuples for each layer. Ah, right. Actually, I need to specify the layer. Wait a second. How do I do that? So I want to have all of the directions per layer, but I kind of want to iterate over them in a simple way. Maybe I can actually change this structure a little bit. So we have layers and positions, and I want to return just tuples. Like, I kind of want to expand, so I want to have a tuple for every position in each layer. So that is going to be the DD and the X. Wait a second. this is going to contain our deltas, right? So if we unpack the items in our neighbor list, then we're going to have the deltas and we are going to have the layer. We'll call it, yeah, DD. And what I want instead is I want for every delta a tuple. Okay. So I'm going to keep new neighbors here. I'm going to actually create a new list. So for all the, I'm just gonna copy this here. That's what I'm going to use in the end. Maybe the deltas for each DD and delta in that thing. And then for all the... Oh yeah. I'm a bit confused about what I'm doing exactly here. I want to return like the delta... Yeah, for all the deltas in that other thing. Maybe like this. Yeah, like this. But probably I'm doing it way too complicated. If you have any idea what I could do instead, then please let me know. But what I want to get is kind of a delta and a dx and a dy here, like this. Or maybe like this. Yeah, that's what I want to get. So now I can use the new neighbors. I think I just reformatted my code and broke some things. It should be like this. And then this is in the loop. Yeah. And then at the end we're going to store the grid. Right here. Okay, let's run it. Now we have a syntax error actually. Maybe it's... Ah yeah, it's because of this tuple here. Grids is not defined. Oh really? Well, let's have a look. That is in the end, and it was reformatted by accident like this. And now we cannot add some things. Okay. I think probably I messed this up completely, so let's see. You can remove one of the for loops in that DD deltas line, you think? Here, yeah, this is not doing anything, right? But that means... No, this is incorrect. Ah, yeah, I see. Hold on. Yeah, I realized that this is not doing anything, really. It's just the same, just returning a level and the deltas. But if I remove that, then basically it means that this is going to be a list of deltas and not a single delta. Ah yeah, I know, I have to do something like yeah, I know what I need to do. I need to do something like this. DD and delta for delta in deltas. Something like that. Yeah. That is what I need to do. Yeah. Okay, have a great night, Fuzzy McFuzz. Thanks for hanging out. And see you tomorrow, hopefully, on the last day of Advent of Code. Good night. Okay, this looks a bit better. So for every delta, I am iterating over it and returning a tuple with the depth difference and the position difference. Yeah. Okay, now we get a small problem. Let's run it with debug mode. And why do we not break there? Here another weird PyCharm bug, but now I get lists. Oh, I do? I think you want to remove this thing. Oh, wait a second. Yes, I have one too many things around. Like, oh no, wait, that was correct. Do I want to get lists? No. Oh, I want to flatten that kind of. So that means that I should actually, I should use a double for loop in this case. So for delta in deltas, and then I can remove this thing here. Now I get a flat list, right? Yeah. So actually you do need to use double for loops sometimes. And now I've maybe flipped it around, I don't know. And where do we get an error? Here? Wait, how can we get a key error? Oh, we get a key error. Where exactly? In line 160. So neighbors contains yeah, and there's one coordinate that we should skip, and that is 2, 2. Maybe we can skip. If x is 2 and y equals 2, then we're going to continue. Oh, 2. Alright. Now, the dictionary size changed during iteration. That is correct and expected. So that may not be valid. Then we'll see about the levels that we have. We'll just store it first and then run over it. And we still get this problem. Oh, the keys is actually kind of a reference to the dictionary's keys. So let's do it like this then. This is a nice hint. While range. Oh, while range is my own invented way of repeating something many times. Maybe this is the better way to do it. Wait. 4. Yeah, that's funny. Okay, so it's running once and crashing. Okay, now what? So how many times did we run? This is one step. And here we're checking some neighbors. Let's see actually if that works. So, well, we are checking now the neighbor at the x0 and the y1. Why don't we check first 0, 0 actually? Shouldn't we? Why do we start with dy is 1? Maybe because of the order I made here. Yeah, we're first going down and then to the right. Okay, that is fair. And checking if that has any living neighbors. And what do we see? The level that we're checking is our same level. And this is what it looks like, by the way. We're checking here down, basically. And let's see if we count any bugs. And yes, we do. The bug count is now 1. Ah. Yeah, that is fine, I suppose. Yeah. I'm just thinking if we should iterate over the depths within the XY loop, but it doesn't matter. We're actually extracting bugs from different levels, so that should work. Okay, so what I want to do is I want to print our grid every time. So let's print our level D after every iteration. And we're running it. Let's run it on the example and see if it works. So this is after 10 minutes. Okay. Unfortunately, we only get output after 10 minutes and not after 1 minute, which I would prefer. Let's also print which step we are, with some nice lines. Wow, we get a lot of depths actually. Not sure if that is okay. I want to do 10 minutes also. So depth 0. So at first, after step 1, we don't have any changes in the other levels. Is that fair? I think that is not fair, because we also need to iterate over the depths that we haven't explored yet, like the one above and below. So I would do that. So actually we need to look at the first level where there are bugs, maybe. Because what happens if we start with a completely empty grid? I think it would stay empty, right? If that is not the case, then our depth scanning should go a bit differently. We only get a bug if there's no space and there's exactly 1 or 2 bugs adjacent to it. Yeah, okay. So a totally empty grid would stay empty. So that means that we do have to check the first level above the level where we have some bugs and the first level below the level where we have some bugs. Alright. So for part 2 we need to think about which levels we're going to check. And those are the depths here. Let's see. Let's start then with depths to check is a list with only a 0 in it. And a -1 also. And a 1. Yeah, like that. And then if we're adding something to a grid that we didn't add before, then we're going to add that depth to the list of depths. Maybe I'll just make it a set for some reason. Or maybe not. Maybe I'll actually keep it a list. Or a DQ. Like this, right? Import DQ. Because then we can append to the left and the right. So that we get -2 on the left and 2 on the right. So we're going over all of the depths. And now how do we know if we're adding to a new grid level? Maybe I can just like grow every step. Maybe that's what I can do. Maybe it's a bit too eager, but I'm not sure if we can easily calculate whether or not we need to check a depth. So after every level, I'm just going to append the lowest one to the depths. So left, append left, and I want to append to it first one on the left. Can we peek left also? We cannot peek, we can pop only. But maybe I can just do 0. So on the left we'll append a level lower and on the right we'll append a level higher. Append right is just append, I guess. Yeah. Okay. Let's see if that helps. DQ expect at most 2 arguments but got 3, so I need to pass it a list instead of a bunch of arguments. And now it says DQ mutated during iteration. Come on. Then we'll make it into a list. like this. Oh, look at that. Our depths are crazy now. How can that be? I'm doing only 10 steps. Oh, I'm doing it for every grid level instead of after every major loop. Like this. Okay. So after 10 steps, we are printing all of the depths, and depth 0 has some data, but depth 1 doesn't. That is definitely not right. We have -1 also. So our bugs are not propagating to other depths. And why is that? Let's look at depth -1. We do start with -1, right? Yeah, we do. That is right here. Yeah. So we'll start with depth -1 and checking if we have any neighbors. I think for -1 we might not find neighbors. Not so sure. -1 is the one on the outside, right? Oh. Wait a second. Oh, yeah. Oh, I think I made a big mistake, actually. Tile 8 doesn't just have one neighbor on the bottom, it has like 5 neighbors on the bottom. So there's a big mistake. So we need to look at the second line. Row 2. Here's row 1. So on the second row we have the middle tile, and that one has a lot of layers, a lot of neighbors. But how do I spell that? I cannot say it's like down, 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 right? Because it's actually not relative. Oh man. It's not relative to the... Oh. I see now. Okay, so our positions are not relative to our locations. That is a realization I didn't make before. So that means that right, left, and down, and so on don't actually work. We have to make it explicit. How can we do that? For the ones on the same level, that is not a big problem. For the ones on the same level, we can basically just add... let's see if we can... How can we do this? So these are all the positions where we are looking at the same level, right? And for those cases, we need to add to those deltas our original position, which is this one. And now we have a problem that we cannot actually add tuples like this because our code is not made for that. And now we need to do it also for a few of them here. I think I'll just do it by hand. So like, oh, oops. So these 3 would all be added also here to the delta. So I'm shifting now from delta based neighbors to absolute neighbors. Like that. And maybe I can convert all of my tuples into some kind of thing that like a name tuple or a class where we can actually add things. That would be handy. Okay, or of course I could have done it in another way where I would say for all of the neighbors on the same level, we would just append the current position to it, or like add the current position to it manually, and for the other positions I'm going to make them absolute. I think that is a little bit more simple to do that. Hey Sup, how are you doing? Did you finish part 1 or part 2 of today's puzzle yet? Okay. Yeah, I'm doing pretty good. Working on part 2 of Advent of Code, day 24 right now. Okay, so for all of the same level neighbors, I'm not going to add anything, and for the other ones, I'm going to make it explicit. So, puzzle, yes, we are doing Advent of Code. Have a look at adventofcode.com to learn more. Here's the link. It's a daily puzzle that comes out on every day till Christmas from December 1st. And every puzzle, it's a programming puzzle by the way. You get some input. The input is unique to you as a participant. And you need to apply some algorithm that you have to come up with yourself and provide the answer on the website, and then you'll see if your answer is right. So I just solved the first half and I got 1 gold star. And also you can see on the top some of our viewers are on the leaderboard, and you can see there who has already solved the puzzle for that for the current day. And a silver star means you solved the first puzzle, and a gold star means you solved the second part of the puzzle. So that's it in a nutshell. If you want to participate, have a look. Day 24 is really quite tough already compared to the other puzzles, because they do kind of go up in difficulty. So for the neighbors on another level, I am going to use absolute positions, but actually I don't need to do that for the layers that go up, right? Because from here, oh no, I do. So from this position, let's look at it here. The neighbor on the top is not actually this neighbor, it is this neighbor. So basically at every place where I had boundaries between layers, I kind of messed it up. So when we go up from the one in the top left, that is this one, then we end up in position 2-2 of the layer above. So that is 2-2. And when we look on the left, we are ending up in position 2-3. Yeah. Okay. That's going to be a lot of manual work. On the right side, we have actually the opposite, which means opposite is not so clear now, but it should be 3-3. No, it is 3-2 and 3-3, I guess. Let me just double check that. No, that is actually 4 to the right. 0, 1, 2, 3 to the right, and 0, 1, 2 down. I think I made a mistake here with the A. Oh no, it is actually right. Man, this is just so confusing. Very, very confusing. Yeah. And so for today's puzzle, we are dealing with a sort of Conway's Game of Life simulation, where we have cells with neighbors. That's pretty straightforward, but it's a kind of recursive world where the middle cell contains another grid of 5 by 5. So cell A has 2 neighbors here, but also it has neighbors on its own level. So the outer level is kind of up from the other level. Maybe I can give names to all of the cells, like here. Let's do that. Let's make a list of the names, and I'll use my iterator here again to generate it. So I want to go from over X and Y, and for X and Y I'm returning just I know what to do. I'm going to give all the cells names just like in the example. So the name would be X, let's say Y times 5 plus X, and the value there would be like that, maybe +1. So now we get a nice dictionary of cells that looks like this. So now we can reference cells 1 and we get basically this position. Python is your own choice. You can do it in any language you want. Some people are doing it in Excel or SQL or Haskell or Kotlin, Ruby. Can be anything you want. Now I'm using Python because for these kind of problems it is my preferred language. Oh, Minecraft even, wow. So there is no limit to how crazy you can be on these puzzles. Okay, so I'm very bad at remembering numbers, so now we have cells that we can reference. So cell 1 is going to be not a neighbor. Before position 1, our neighbor is going to be 2 and 6 on the same level that we already did. And on the level above it, it's going to be 8 and 12. So cell 8 and 12. Can we actually select multiple items from a dictionary in Python? Like in R, for example, if you know R? Like let's say we have a dictionary like A and B. Is there any way we can get both A and B out of it, but not C, for example? Ah yeah, with a with the comprehension, of course. We could do like ah yeah. I'm not sure if it's going to help, but like let's say we want to get the value for all the values in the dictionary. This one. And then if the key is in 1 or 2. Nope. Then we need to say items. But that doesn't work. Oh, not 1 and 2, I meant A and B. Yeah. Okay, that works, kind of. It's not that super clean, but let's do it. So that is a position for K and P in cells dot items if K is in 8 or 12. Right? Maybe I can make that into a function. Let's call it get neighbors with a list. Okay, and that's just what I'm going to return here. And here is the indexes or the names of the neighbors. So get neighbors 8 and 12, and I'll make that into a variable length arguments thingy. So we're getting the neighbors 8 and 12 for the first one. That's A. For B, we're getting the neighbor 8. For C, we're also getting only neighbor 8. And for D also. And then for the other one, for E, we're getting neighbors 8 and 14. Yeah, this is easy to make. Now it is easy to write all the right neighbors. And for row 2 on the left, that is basically this F here, we're going to have neighbor 12. And that is going to be the same for K and P as well. So here we have -1 with neighbor 12. Oh, hold on a second. Is that correct? Yeah, okay. So the neighbor's position is actually exactly the same for those few cells. That is a bit kind of counterintuitive, but I guess it is correct. And on the right side, we have neighbor 14 actually. So here it should be 14. On the second row, right? We're doing this row. Oh, I think I'm messing up a little bit. For the second row, we have only 12 on the left and 14 on the right. Like this. And the other neighbors are all on the same level. So G, wait, why am I saying G? Yeah, G has neighbors all around it, but F has neighbors on the top right and bottom. The top, right and bottom, up, down and right. And then the second one has no neighbors on another level. Like this. And 2 to the right on the first row, that is H. It has a neighbor somewhere else. It has neighbor, so that is equivalent to this cell actually on the outer layer. That one has a lot of neighbors like 6, 7, 8, 9 and 10. And then the last item on that row, that is J, that has only 14. And for the third row, we have on the left neighbor 12, and we have it as well for the row 4 on the left, and the last row there we also have it, but we have something more, so I'll keep that for later, or maybe not. I don't know anymore. So on the last row we have U, it has a neighbor 12 and also 18. Now for the second line, we're now in the middle, checking tile L. It has only on its own layer 3 cells, and on the layer below it has basically nothing. It has nothing because basically L is equivalent to 12 in the outer layer, and on the right side there is, oh yeah, wait, there are neighbors. There are A, F, K, and P and U. A, F, K, P, and U. So it would be cool if we could actually reference those with the same letters. So if this was cell indexes, and we had also cells by letter, that would help. So instead of using value, where did we generate it? Here we generated it. So instead of using this, we'll just add a 65 and turn it into a character like with CHR. Then we'll get it like this. Yeah, and now I kind of want to append it to the other list. Maybe we can still call it cell names and append to it. Extend, append from keys. How do we kind of extend the dictionary? Maybe just plus, like this. Not sure if that works. That would work if we had, like, let's say 1 with 42 in it, or 52, and then another dictionary like this. No, we cannot add it. Python append dictionaries. Well, I know another simpler way to solve this problem, which is just to remove the ending parenthesis of this one and removing the first one here. Now we also have 2 dictionaries combined. So I realize now that, yeah, neighbor cell 8 has cell A, B, C, D, E. So I want to call that like A, B, C, and D as well. A, B, C, and D. And split it by nothing, but that is not possible in Python. So I have to do it like this. Nice. Which other cell are we talking about now? Okay, so the third row we have tile 12. 12 is 1,2, right? We can see it here, 1,2, yes. That one has A, F, K, P, and U. So here we have get neighbors, and we can do A, F, K, P, and Q. And the tile on the right of the middle has E, J, O, T, Y. E, J, O, T, and Y. Now, the one all the way on the right has on its own level up, down, and left, and on the level above it, then it looks equivalent to O. It has tile 14. Right? Yeah, it looks symmetric. That's a good sign, because it should look symmetric. Row 4, that should be similar to row 2. So that means that we have neighbor 14 on the right for the last item in the row. Is that correct? 20 here is equivalent to T, and that is row cell 14, yes? Now what? 17, 18, and 19. So 17 and 19 have all neighbors on the same level, and then the one in the middle has a whole bunch on a level above. Those are called U, V, W, X, and Y. And now the last layer. So the one in the bottom right corner is equivalent to Y, and it has 14 and 18 as neighbors. And the one on the bottom left also has 18 and 12 as neighbors, yes. It's a bit strange that cells on opposite sides have the same neighbor, but that's how it is. And then cell 22 has neighbors on its own level and one above it, so it's equivalent to cell 4 V. It also has cell 18 as a neighbor. That is the same for all of them here. Wow, okay, that was it. That was very boring. It took a long time to write all of this down. I hope that this is going to be fixed. So we have 5 bugs in total according to our algorithm. That doesn't sound right. So I guess our total bugs is something we're not calculating correctly. We're checking all of the grids, which makes sense. Maybe we should check depths instead. I don't know. Now we find no bugs at all, actually. How is that possible? Do we reset depths every time? Well, we reset it only once. Okay, let's see what happens. Why do we find only 5 bugs? Even though we have a lot of depths with bugs in it. So here are all of our grids, and we do create new grids every time. So we should not have any reference problems. Maybe we should print it again afterwards. Because now we're actually printing. Yeah, we're printing the level after it was updated, so that is fine. I'll just print it here also. Oh, we're always printing 0. Why is that? Oh wait, we are printing it for every X and Y position. So we do print like a lot of depths. We do see at -9 some bugs, while at 8 there are no bugs. Okay. And we're having this add function here that looks a bit weird, but it should be fine. And we don't need to break at every step in the loop. So here we're checking if there is a bug at where? At D, which is 0. It should be 0, 0, 0. 0. Yeah. Let me add another watch variable like d, x, and y. Okay, there are no bugs there. And G, you have solved part 2. Nice. Going strong. And why am I starting with level 0? Shouldn't I have a level -1 as well? Yes, I do have a -1, but we're not iterating in order. So let's iterate over the depths instead. Hey Bruno, good morning. Yeah, you're finally up early enough to be live on the stream, and I am slow enough so that you can still join. Good morning. How is it going? Thought you would use your personal simulator. No. Well, I made a cellular automaton last year, but it definitely does not have support for recursive grids. So I have to implement something from scratch. And are you working on the problem as well? Did you solve part 1? Or did you just wake up? Bruno is my colleague, by the way. And he is also the most motivated person on Advent of Code of all my colleagues. And you solved it. Oh, wow. Okay. That might... Yeah. So now I'm not ahead anymore. Let's have a look at what is going wrong. We're starting with layer -11, and there should not be anything there. Ah, you reused your Game of Life codes. I think you made a generic like solution to cellular automatons as well, with some way to implement rules, right? Okay, -1 doesn't have anything, and let's break until we have a level with something more interesting. Like here. So -9 happened, and then we have -8, and let's count 8. We have 1, 2, 3, 1, 2, 3, 4, 5. So we have 8 bugs on that level. And we're checking all of the ranges. And oh, I see the bug. The bug was that I'm iterating over all positions till x instead of the width. And yeah, I see how it's helpful if you have that solved before. And was it generic enough to deal with this problem, or which part did you have to adapt to support the recursive grids? Total bugs 156. That is a bit better than before. But it's still not good enough. And I am iterating 10 times, I think. Where is my iteration count? Neighbors I don't need anymore. Here. From 0 till 10. And we have... Oh, look. Here I have a lot of bugs deeply down. And then later no bugs anymore. Okay. You, with your approach of tracking only living cells, just fits this extension more easily than the grid approach. Ah yeah, I guess it does. And then you can just count the set size. That is a lot easier actually. Yeah, I had a few cases where we had to solve puzzles with x and y coordinates, and I started to use sets for them, and it was very handy also to iterate over all of the positions. It's so much easier if you just have sets with x and y coordinates or x, y, z coordinates. But this time I didn't do that. I don't know why exactly. I think I wanted to stay close to the input data structure, which is just a string. Then I figured out that it doesn't work. I have to make it into lists of booleans so that I can actually hash them, and I can detect duplicate states. And that's how I ended up using grids instead of sets of positions. Oh man. Okay, let's print the level number of bugs. Bugs in level is 0, and then we'll add it. Then in the end of the level we'll add that to our total bugs, so that we can debug if our level counting is correct. I think it should be correct, but who knows. Small bugs happen every time. So for this level we had nothing, okay. So let's go over to the next one. Here we should have had one bug, and we did find one bug. Here we find 5, that looks correct. Here we find 8, that is correct also, and a whole lot more. But our levels are a bit different. So here, after 10 minutes, we don't have... So we should have only bugs at level -5 as the first level. And I have -10 or something. So I think that I'm not counting my neighbors correctly. So tile 19 has 4 adjacent tiles. Yes, that is this one. G has 4. Okay, that is this one, yes. Tile N has 8 adjacent tiles. That is this one here. Let's see if that matches with our neighbor definition. So tile N, that is equivalent to tile 14, which is on row 3. That's this one. And on its own level it has 3 neighbors, and on the other level it has 5, so it has 8 indeed. Looks like correct. Yeah, 3 and 5 tiles within subgrid marked question. I really wish there was an example with just one iteration, but I think we can just do it ourselves. So let's look at the first step. So here we start, and this is the first step. So in the first step we're saying that at level -1 we're going to have one bug, and this is cell 8 in this graph on the right, and it has all the cells on the top as its neighbors, but from another level. So -1 means that it's on the outside actually. Yeah, so that means that it has all the cells from the top layer of depth 1 in it. Right, yes. And there's one neighbor there. And otherwise it doesn't have any neighbors, so it should become alive. Right, because empty cells with exactly 1 or 2 neighbors do become alive. So this is correct. But it's surprising to me that we only mark one living cell in depth -1. Because if you look at this cell, for example, which is cell 18, it also has 5 neighbors from the other level, and there's one cell alive there, so this one should also become alive. Maybe the neighbors are not set up correctly for that particular cell, but I think I just checked it just a moment ago, and that's the middle one at position 2, 3, and it has 3 neighbors on its own level, and on one level up it has 5 of them. Yeah, that looks fine. Maybe I'm doing the up and down a bit wrong. So, yeah, this is one level up. So from level 0 we go up by 1, so that our new level would be level 0, and that's where we're going to check neighbors U, V, W, X, and Y. So we do check that correctly, but I think it's not working still, so let's set a breakpoint where we are counting the neighbors, and that is going to be here. I hope that this breakpoint will work, because it seems that my editor doesn't want to break on points where there's only assignments going on for some reason. I know why. I know why it doesn't work. I replaced my X and Y with I replaced my deltas with absolute neighbor positions instead of relatives. So I should just use neighbor X and neighbor Y. I forgot about that. It took so long to write down all the neighbors that I completely forgot about this part. And if the delta is the delta for the levels is 0, then our neighbor X and Y is still going to be relative. So then basically we apply this formula as before, but now we have well, it's yeah, the neighbor X and Y is now relative, so we should add to that our current X and Y position, and otherwise we will take them as absolutes, so we'll just pass. And the layer is always relative, so that is a bit better. And we don't get 99 bugs yet, but maybe this is an improvement. Yeah, now you see that the one on the bottom is also becoming alive. Let me double check my neighbors list. Yes. So we use relative positions for all the neighbors on the same layer. Okay. And then we also have a check where we say if we're in the range or not. And this check is still the same. Yes, it is still the same. We don't need to check for the range of the layer. That is infinite. Okay. So after our first iteration, maybe we can actually draw it out like completely by hand. I will do that. So I was gonna say let's switch to the whiteboard. It looks like my whiteboard turned off. Ah yeah, it turned off while my stream disconnected because my internet actually dropped for some moment. Oh, there we go. Now I can draw. And I've already asked my supplier of the whiteboard software to remove this really ugly interface that sometimes pops up, but they said that they have no way to do that and they're not gonna do that. Unfortunately, if I'm not careful, you're going to see this happened. That is actually my notes for another for a book that I was reading. Alright, so we have our grid 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and in the first iteration we have an X here, here, and here also, one on the left, two on the right, one in the middle, and one in the bottom left. And our next iteration, this is the question mark. Our next iteration should look as follows. 1, 2, 3, 4, 1, 2, 3, 4. That should look like this. Okay, so we're checking all of our cells. This one has one neighbor, so that should become alive, right? I think that is as simple as it is. One neighbor means becoming alive, so that is a check. I'm using a little bit more bright color. Then what else? The second neighbor here has no neighbors around it on its own level, and on its level above it, that would be that is a bit hard to visualize, right? Maybe I should also draw a kind of nested grid as shown on the manual. So we have some here and some here. It's very hard to draw this, but we'll get there. 1, 2, 3, 4. 1, 2, 3, 4. So we were checking the second grid item, which is here, and it has the middle one as its neighbor. So, well, on the outside there are no grids yet. We have no levels above us at this moment. So basically that one will not become alive or anything. Next one here, we have nothing around, so that will also be empty. Then the third one has 2 neighbors around it. That means it will become alive. This, the last one here, is alive and it has exactly 1 living neighbor. How did that work again? A bug dies unless there's exactly 1 bug adjacent to it. So this one is alive and it has 1 bug around it, so it won't die. But what about the top and the right? Those are on the upper layer and that one is completely empty for now. So or is it empty? Maybe the upper layer is the same as our own layer. Maybe it is just like that. Is it like that? Because since I've started this puzzle, I haven't figured out whether the other layers are empty or not. Diagonal is not adjacent. Okay, so a few of you have pointed out that the top right one does not have direct neighbors. Oh yeah, right, you're completely right. I should not look at diagonals, but that was just a bit of a brain fart. Thank you for that. I do appreciate like correcting these silly thinking errors. Yeah, I think it's not really the point of solving the puzzle to check whether you make no mistakes for 2 hours in a row. Okay, so this one has no living neighbors, so it's going to die, and that is, I will mark in, how should I mark it? Maybe a small X. Alright, now the next one here. Yeah, okay, so then I think I understand the logic correctly. This one has 1 neighbor around it, which is fine. On the outside, it's an outer layer, so I'm assuming no bugs are there. Can I ask a question? The outer layers and the inner layers, are they all empty to start with? Or are those layers ourselves? So like, is this one connected to this position on the same grid? Meaning this one? It's empty. Okay, thanks. Okay, only layer 0 has bugs. Yeah, I was looking around it. I was looking around in the instructions, but I couldn't find it without actually reading everything again. Oh, initially no other levels contain bugs. Okay, right. So we've already established that after 1 step we should have 2 new bugs on level 0. Oh wait, I am checking level 0 and there we do find something. We do find that... Oh, was that checking level -1 or level 0? Now I forgot. I think I was just checking level 0. Yeah. And Alex, you found it hard to debug this puzzle today because the example was only given after 10 minutes. Exactly. Do you want to have the state of the example after 1 or 2 days or so? You mean you would provide it to me? Maybe. Maybe. But I think I've already found a bug actually in the code. So I'm gonna try to solve that one first. So, minutes, yes. Minutes instead of days. So after we look over depth 1, here we should have... So in my example, I'm calculating 3 bugs and that looks wrong. Let me double check that. We should have 1 on the left. Now again, this stupid overlay comes up. So here we should have 1 and here definitely should be nothing, right? Because we have no neighbors at all. Okay, so why does that generate a bug in our code? Okay, so we're going to iterate over level 0 and see what happens. How can we do that? We can put a breakpoint whenever there is dd of 0, and Ah, but DD being 0 means just that the delta for the levels are 0. So I want to break when the actual level is 0. So let's do that. When the neighbor delta... Oh! No. When this delta with this depth is 0, then we want to break. So a lot of different levels here. Like this. And when D equals 0, then we're going to break. Let's run it. So D is now 0 and we are checking for the neighbors, and let's see if the cell is going to be dead or alive. We're saying that when we go down... No, hold on a second. We are counting all the neighbors, right? Where are we counting the neighbors? Here? Oh, I know why. I accidentally moved this one level too deep. That is something that would never happen in Java, because you would have to move your code in between curly braces. In Python that can happen so easily, especially when you do something like this, removing a for loop and then reformatting your code. That's what I did. Okay, so that was our bug. Now let's run it. And we still get something that is not entirely correct. And we assign our grid after going over all of the ranges, right? Yes. So if we have a bug at X and Y, that's where we are, and we found not one bug, then we're going to not be a bug anymore. That's it. Okay, so I'm still going to have to put breakpoints here because it doesn't seem to be correct. So if the depth is 0, what do we actually get as an output this time? The depth 0 still looks as it was before. That is a bit strange. Even though I changed my loop, I changed my checking to happen outside of the neighbors loop. Alright, so we have an X and a Y position of -1, 0, and 0. So that means we're now checking. No, we're already out of the neighbor loop. Oh, hold on, this is D. Okay, we're actually at depth -1 right now. Why is that? Because we're breaking inside here, and I don't want to break there yet. I first want to go to the right breakpoint and then check what is going on at that level. So for the first position, which should be 0, 0, we decide that we're gonna keep it the way it is because no rule applies. That is definitely not correct. And the bug count that we found was 3. And we found 3 because what exactly? Because we have all of our neighbors, and those are the following. We have 4 neighbors for the one on the top left. That is correct, I think, yes. And we have one on the outside, and we have 2 on the outside and 2 on the inside. And what else? Oh, I know why. I know why. Our new grid function actually copies the original one, no? No, it just returns false. So that's not the case. Now I need to activate my breakpoints again. Can I copy this breakpoint to another place? No, I can't. Alright, so these are our neighbors. And how many neighbors do we count? We count 3. But why? Good morning. Let's see, so if the delta is 0, then we're just taking the neighbor position as it is. You can copy the condition inside the breakpoint. Oh yeah, that's, of course, that is a good one. Yeah. then I don't have to then I don't have to remove and add those breakpoints every time. Like that. Yeah, I actually do want to go over this loop here as it happens. Okay, so here we are. So our nx and ny are shown here as 0 and 1, and the depth is 0, and we're checking for all of the x positions in the range. Oh, no, if the x position is in the range and the y position is in the range, and if we have a bug at that grid point, then we're going to add one. And so our nx and y is, let's call it nd and nx and ny. That is now 0, 0, 1, so that is 1 below our current grid point. And for a grid that looks like this, that means that we're checking this position basically, and there should not be any bug there. At least, wait, originally there was a bug. Actually it is correct, so there should be a bug. And that is true, so we're counting 1. Now for the next position, that is... Oh, I think... Wait a second. Was I just going down? Yes, I think I was. But here it looks like I'm going now to the right. Okay, yeah, that's correct. So I'm going one step to the right and not down at all. And in that grid, one step to the right is empty, and we should count nothing. Oh yeah, now we've actually determined the right value for nx and ny. And do we have a bug there? No, that's also correct. Now, what are we doing? We are now looking 2 to the right and 1 down, but it's on a different grid. So on the other grid, let's look at that one. And do we get true or false? It should be false. It is true, but why is that? So we have grids here, and it contains some truths in some places. Can it be? Oh yes, I know why. I know why, because we did first depth -1, and after handling the depth, we are saving it directly into the grids. And that is not allowed, because we have to wait until we've handled all of the grids before saving it. So I need to keep a list of new grids that is going to be empty every time that we run an iteration. So the new grids are here, and I'm going to make it a dictionary, maybe? Yeah, a dictionary. And then we're adding it to the new grids here. For D, that is the new grid. And then at the end, we're going to replace all of the grids. So for G in new grids, we're going to save it. Equals new grids G. Not sure why I call it G. Oh yeah, for grid, maybe. Maybe I should call it D actually, instead. Okay, do we have something better now? The total count is now 27. That is not right. Maybe I'm not in the right loop now. After every step I should do that, right? So that means right here. 117 bugs. Well, we're getting closer to 99. Still not exactly there. But after our first iteration, our new grid looks like this, with only one bug all the way on the right. That is still not So we're saving to end grids, and then in the end we're storing it. Okay. Well, for every depth, that's what we're doing, right? Let's look at this loop. So we're storing the new grid into the list of new grids. That is looking fine. Maybe, yeah, this is cleared every time, so that's also fine. And our grids are always fresh, so we don't have reference errors. I think I need to go over the loop again and break. So let's go until we see what exactly. When are we gonna stop? Looking to the right at the same level on layer 0. There we should find no cell. We are looking at 0, 0, 0, and we're looking at 1 to the right. There we should find nothing. Let's see if that happens. So this position should be false. And we do get false, but that's fine. Then the next one is 2 to the right and 1 down. And the level is -1. That should return false. And it is false, but that's fine. Then the next one is going to be level 0, same level as us. Oh no, that's where we are, and the level we're checking is 1 up, and then at some other position, and that should also be false. Yeah, let's break every time we're counting. Let's do it like that. If D is 0, then we'll break. So we didn't count anything for this particular neighbor, for these neighbors, and so we counted in total 1 neighbor. I think that's what we concluded before as well, so it should become true, I think, and it does. So our new grid is now true for the first cell, and everything else is false. Okay, now for the next neighbor. That is, after normalizing the position, that means the one on the top left, that is empty, and the relative layer we're checking is our current layer. So that didn't match anything. Is that right? Oh, hold on a second. What is this grid? Oh, I think I'm completely reusing always the same grid rather than grids. Ah, that is a problem. We need to check all of the grids with the current grid. Ah, that's just a very simple bug. Not sure why I make those bugs. Carelessness or trying to do too many things at once. So that is actually what went wrong. Always reading the same grid. And now I want to make sure that our grids is initialized with our original grid at first, and that's what I'm doing here. So that should be fine. Now we get 98 bugs. Okay, well, almost there, I would say. How come you print 3 dots after the question mark on empty layers? That's a very good question. Oh, here, I see. I'm actually right at the correct point. I didn't make an else statement. That's why. Oh yeah, I didn't even notice that before. Thanks for pointing that out, yeah. So we have 89 bugs, and why didn't we catch the last one? So after 10 iterations, depth 5 looks exactly like this. After 200 minutes or after 10 minutes, this is what we get. Depth 4 looks like this. Oh, here's a bug that I am showing where there should not be one. Okay, so there I'm calculating something wrong. Maybe there's just a tiny error in my neighbors list for that position. So that position is the middle row, and then the one on the left of it. Right? That's this one. And we're saying it has neighbors above it, on the left of it, and down. And on the right side it has A, F, K, P, and U. It should be U instead of Q. So that was it. Did we use Q anywhere? No, and we shouldn't either. Okay, now we should get 99. Yeah. Wow, you have to be very, very careful for this kind of problem. And I guess, in hindsight, you know, for the last 20 days or so, I haven't written any tests, and tests could definitely have solved or avoided this problem. I was starting to do tests in the very beginning. Yeah, thanks, Alex. I wanted to do test-driven development a bit to make sure that I'm not making mistakes, but for some reason, as I went on and on, I totally forgot about it. And yeah, the problem is to be very, very precise, and I agree with that. So let's run it now for 200 minutes. Where did I say 10? Here's range 10. Maybe I'll say it as an argument to part 2. Here. It's also a bit of a long, messy function. So 10 minutes by default, unless we say 200. And then we'll use the original input like this. Alright, let's run it. 200 minutes going on. And it looks like it does take some time. Maybe I don't want to print the levels every time. So we can run it faster. But it's already done. And we have 1923 bugs counted. And it is right, yeah. Okay, well that took a long time. And let's look at some statistics for today and see how many people have solved it. Oh, that's quite alright. Yeah, thanks everyone. Okay, so that means that the puzzle was solved, I can commit, and now I want to know how you guys managed to solve this puzzle without so many bugs as I had. Perhaps you have more clean data structures, or you're doing it in a more simple way. Thanks Alex for sharing your code already. So this was day 24, part 2. And we're going to have a look at what Alex did today. Alright, yeah, you see, it's 57 lines of code, and I made like almost 4 times as much. And I always think that making too much code is the reason why I am having bugs, but I'm not sure. I'm also writing code to make things more clear in some way, but the more you write, the less of an overview you have, and every line of code has a chance of bugs, of course. That is something we have already learned the hard way. Oh, you had 30 more bugs than my answer. Yeah, that makes sense, right? We all have different inputs, but it's kind of similar then. So let's copy this. Give it a bit more space. Yesterday I had very weird errors where I couldn't run someone's code because of an import going wrong. Today I hope I'm gonna be more lucky. And yeah, here's another part 2 with an input. Oh, I think, Bruno, I got confused about the meaning of bugs. You had 30 more bugs though. Yeah, I mean, you said how we solved it with less bugs. I meant programming errors, not actual bugs. Like, maybe you should have used ants or something. I meant, how did you solve it with less programming errors? And yeah, G also understood my remark in the same way as Bruno. Yeah. Okay, so we have an answer, 1923, and here is the other answer, and that is the same as I had, I think. Yeah, it was funny listening to Bugs and Bugs. Yes, very confusing. Okay, so Alex, how did you solve it? Let's have a look. Reformatting. So it looks like the way I'm used to. So you're actually using a dictionary, or oh, this is a set. Isn't it a set? When you use parentheses with no colons, then you're getting a set, right? Let's look by debugging. So bugs is a set indeed. Yeah, so that is actually something that I learned right now, that a set equals something like this with a 4 in it. For x in range 100, for example, that becomes a set. So those are all of the positions, and then what happens? You're having a history where you keep track of all of the sets that you found before, and you have a sum of... yeah, that's also a lot easier. To calculate the biodiversity, you can just iterate over all of your bugs with x and y coordinates, and you're doing a power function which has double stars instead of pow. So that's also something I learned that is the same as pow, not exactly 2 to the power. And then when you found it already, then you're returning it directly, and you're returning the number of the diversity level. And so how do you calculate? Wow, that looks very short. So you're going over all of the bugs actually. So instead of going over all positions, you are just going over all of the bugs. And do you keep a state for the new set? Doesn't look like it. So you have all your neighbors, that is left, down, right, and up. And then if, hold on a second, this is a double range check. So this is a double range check. You're checking directly whether I plus dy, and that means the neighbor's position, whether the neighbor's position is in the right range, and whether it is in the right y range. So that's another thing I'm learning here. So I is in between, let's say, I is in between 0 and 5. That equals, that's the same as y in range 5, for example. So you're checking the ranges, and then what are you doing now? You're having a counter, and I missed your initializing a counter which counts integers. And oh, yeah, okay, so it's a default dict, so you can put anything in it and just count stuff. And so you're counting the neighbor's position and then adding 1. Oh, but how does that work? So you're just keeping track of the number of neighbors. Okay, that's all. You're keeping track of the number of neighbors. And then your new bugs after 1 iteration is going to be a new set. So you have a set where you're going over all of the items in your counter, which contains, what does it contain? It contains a position and a count of the number of neighbors. And then if the count is exactly 1, then you're keeping it, so you're keeping the bug, and otherwise you're keeping it if there are, if not boolean bugs and count is 2. How does that work? So I'm not sure how you're generating. So this is a very different algorithm than what I was doing. You're actually adding bugs to neighbor positions, aren't you? B can also be a position where there's no bug. The biodiversity is unique to a grid, yes. B can also be a position where there's no bug in line 19. Yeah. Okay. Right. Let me try to write it on the whiteboard or blackboard. Because I must say, to think of it conceptually is a little bit different from normal, from the way I made it. So let's say we have a grid. And there are some bugs on the grid. So let's say there's one here, and one here, and one here. So then we're going to iterate only over those positions. So I'll highlight it like this. And then, let's see. So we're starting with this one, and we're checking all of the neighbors. So that means that we are going to look at positions up and here, and we do find that one on the top is not valid, so we have all of these, and then we're keeping counts, and we're keeping counts per position on the grid. So we basically have an extra sort of grid. I'll draw it here in light, and we're keeping counts. So this position here has a count of 0, but then how do we count? Wait a second. We're actually counting. Ah, now I see what you're doing. You're counting for every neighbor on the grid how many bugs are next to it. So that's what you're doing. So that is actually very interesting. So you're counting one here and one here and one here. And for the second bug, this one, you're also keeping track of the counts. So there's one above it, so that will be +1 as well. And one here and one here and one here. And then for this bug, you would have +1 for all of them around it. So that would be 1, 1, 1, 1. So that's in the end. Then you have a grid. Looks like this. Let's write it. 1, 2, 1, 2, 2, 1, 1, 1. Okay. This way of running the simulation should be much faster than iterating over the positions rather than the bugs. Ah, cool. Just need to turn off my turn on my do not disturb because my watch is vibrating every few minutes. There we go. It should be much faster also, yeah, because you're not iterating over all of the positions. That helps. Are you sure about that? If the grid has a lot of bugs, there will still be a lot of iterations. Yeah, but you would not have more iterations than if you would iterate over every position, right? I think. Because in the end, here, you're getting a counter that has no more positions than the grid. Alright. Now, so let's see. Oh, it looks... So we have all these counts, and then we're going to iterate over all of the counts. Like this, 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 and such. And also we need to still remember that here was a bug originally, right? So we do iterate over all of the counters, yes. And we get a position and the number of items. And then you're saying if count equals 1, let me just write down that code, how it looks like in the code. If count equals 1 or not b in bugs, that is the same as b not in bugs, I think. No, that's not the same. So not b in bugs, and count is 2. Like this. Maybe for part 1 it doesn't matter. Who knows? The not is inside. So you mean not be in bugs means be not in bugs. Is that the same thing? We can also... Well, can we test it? So the way I wrote it now is not correct. You're saying that it should be not in bugs. And C equals 2. Like that. Okay, so let's take an example and look at one of them. So let's say we're considering this one here. And that is the case that we have exactly one count for that position. And we're also checking if that position is not in the bugs. And that is true because here in this position you see there's nothing there. So it's also not in the bugs. But it doesn't matter because as soon as we find count 1, that means that we're going to have a bug there. So we can just make it alive. But let's look at another one where we have not count is 1, like this one. So here we're seeing that this is false, and we're going to check here this one. And B, is it in bugs? No, it's not in bugs. So that this part is true, and the count is 2. That is true also. So we've checked both of the sides, and then this one can become a bug in the next iteration. I think that should be fine, right? Because we have 2 neighbors that have a bug. Okay. And then you've just created an entire new grid out of that just in one go. And I'm not sure exactly where all the bugs are going to end up, but let's just mark a bunch of them that looks correct. And the bugs that have only one neighbor that can survive, and the bugs that don't, that just will die. Like I think this one will also become alive. So like that. Wow. Yeah, it's a very elegant solution. Very nice. So here we go until the end of the iteration, and we get some new bugs, and it looks like this. And we have 11 in it, so you've already counted it right away. That is very helpful. Yeah. And so I think the key insight here is that if you're going to count neighbors, what helps is to make an intermediate state where you count the neighbors for all of the bugs that you have. So instead of, well, I'm not sure how much it saves you, but it does feel like an elegant solution, like a two-phase counting process. Well, I guess the advantage is that you can create the entire new bug set just all at once, and you don't have to copy anything or append or anything like that. Alright, so for part 2, how does it go? We just keep running it and we open the bugs again. That's just the same as before. And now you're iterating it, that's the iterations, 200 times. And you're counting again in the same way, but now you're counting in a different way than before. And wow, it's so cool that you can just reuse your old code in exactly the same way. It's just that this part is a bit more complicated than it was. So I think you've probably found out the different cases a bit more than me. So I made a dictionary of all the different positions and which neighbors they have. So here you have the normal list of neighbor deltas, and you're checking also again if you're in the same range, but also you're checking now that you're not dealing with the center, and if so, then you're counting +1. But how about the different layers? Ah, I see. Okay, so you're counting all of the neighbors as before. Actually, that's something I could have done as well. So for the same layers, you can count all of the neighbors around you, except for those, of course, that are out of bounds. And then here you're also adding to the counter all of the neighbors around it. And so for I is 2 and j is 1, let's look at the puzzle, see what that was. Let's look at it here. So for I is 2, that is here, and J is 1, that's this number 8. You're counting also A, B, C, D, and E for the next level. And I see your counter is now 3-dimensional. So that is... Oh, you're saying it's 12. So I, J, and L. I is 2 and J is 1. So you're doing Y as the first coordinate and X as the second. Yeah, okay, so you go 2 down and 1 to the right. And then you're counting 5 times all of the positions on the left for the next layer. So you're going over... But hold on a second, you're iterating over X. If you're talking about I is 2 and J is 1 being 12, that means you should iterate over the Y values. I think it's probably just a placeholder and this is not literally an X. Am I correct? Although here you also say that you're keeping a count with X first and then Y. This is actually... This should be the Y value. You copied it without changing the name, okay. And that is basically the Y value being... or the X value. Hold on a second. So if this is really 12, then we should iterate over this one, right? So the X value should be always 0. Oh yeah. And this is the Y value. Let me just rename that. Not to kind of fix your code, but because I will keep getting confused about it. So that is Y. And X is constant, and then you're adding it to the level above you. And you're doing similar things for Y equals 3, or yeah, for the right position, and so on. So I think it looks quite clean. I think it is a lot cleaner than the way I did it. Let's have a look at it again. So here's my neighbors array. Yeah, so he's making a list of neighbors for every bug found. He tells the next layer squares that they have a neighbor somewhere. Exactly, that's a good explanation of it. So once you've decided for every layer that you know about how many neighbors are there or how many bugs are touching it, then you can recalculate your bugs. And because you have all your layers in one set, it's going to be again very easy. Yeah. Okay. And then in the end you're just counting the number of bugs. Wow. I'm wondering, when do you have a very strong argument for using a 2D or 3D grid? Because this seems to make everything so much simpler. And the only case where you want to iterate over all the positions which are not in your set, then you can just make a loop where you iterate over X, Y, and Z in the dimensions that you know. So, and also getting the bug most on the right and on the left, like the bounce, is also a lot easier if you have a set of positions. So from now on, let me remember I'm going to use only sets of positions. Thank you very much, Alex, for sharing. If anyone else has a solution, it doesn't matter if it's quite similar or if it's written in another language like C#. Maybe one of our new viewers has tried to solve this puzzle in C#. And you're very welcome. I learned a lot today again. And Bruno, you like how your bugs tell their neighbors to add one. Yeah, that is a nice way. And also it reminds me a little bit of, how do you call this game on the Windows with the mines? Like Mine32.exe? You know, it has a different... Minesweeper, yeah. So it's kind of like Minesweeper, where every grid has the number of tiles with bombs around it. And basically you're just creating that. And gee, yeah, I do want to see your solution. You have 2 different files, that doesn't matter. We'll see if I can run it. If I can't run it, we'll just go over it just line by line. To kind of keep it separate, I'll make a new folder G and put your solution in there. And Bruno, you have a solution which is also a set, but you gather all the potential next generations, and then each of those ask their neighbor if they are alive. Okay, that's also interesting. So do post your solutions on GitHub or somewhere. And in hindsight, it's way too complex. Okay. Well, yeah, hindsight is always helping us to find simpler solutions, but in the moment it can be hard to see what is the simplest solution. So this is the first file for G's solution. Python file. Oh, no notebook. I was also thinking if you could do it with notebooks. I haven't thought about that. Or I haven't tried that yet, actually. So, 2 files. Is it for part 1 and part 2? Maybe? Okay, yeah, you also pasted your code right away. That's nice. I did that also. Or maybe these were examples. Oh, I think this is just a comment. And you have part 2. And there we go. Part 2.py. Yep, I will change the file names, no problem. But it's day24/inputs.txt. And that's it, so let's run it. Alright, that did run. And we got some output. Yeah. And we get all of the phases shown. So let's go over it in debug mode and see how it works. So you're first actually getting all of the lines. No, you're getting the first line. And you're using read.splitlines. Right. So input.read, what does it give you? It's already closed, so I cannot show that anymore. But input.read reads all of the data into a big string, right? And then you're using split lines. So that is kind of equivalent to input.readLines. And so I'm always forgetting that there's a way to read everything at once. So that's something I'm going to try to remember. You're nicely closing your input file also. And then you're getting all of the... I think this was probably a placeholder code, or in case you needed to parse integers, because this seems to parse all of the digits in the input code and optionally accepting an infinite list of dashes. I think you probably meant to write a question mark. In case you didn't know that, question mark will match with a single character optionally, which is equivalent to 0 or 1 matching characters. Just to add a little bit of my knowledge also to the stream and share a little bit of what I know. So, you have maps, and maps is going to be... What is it going to contain? Okay, it's going to contain a line for every line in the input code. Okay, so we run that until it's done, and then we get a list of characters. And then you have generations, which contains the first map. Ooh, I get a bit confused that it's called maps and not map, but we'll try to keep that in mind. It's a single map. And now you have a function that calculates the next generation for a specific generation. Cool. That is something that could have been useful for me, I think. And so how you're solving it? Map was already used. Yeah, because map is a function in Python, I guess. I guess that map... Let's see how that looks. Map is a class that exists. Okay. Yeah. Then you have to use map_s. Now, let's see. You start with pn of maps, and pn does what? Print. Okay? And then you're doing while true. So you're going over all of the generations. So you generate a new map with next gen, and then you're printing it. And then if you have this exact map already in the previous generations, then you're printing end, and you're done. And then you still need to print the biodiversity of the last map that you found, which is kept after the loop. So let's see how you make a generation. Oh, and by the way, you're also copying your entire input instead of referencing it as I was doing by accident. But I did find that I had to copy also all of the characters inside my map. I'm not entirely sure why I had to do that, but it seemed like I was still not getting clean copies. So next gen is going to take neighbors. I guess neighbors and other neighbors. What does it contain? Oh, I jumped over it by accident. So let's run the code again until that point and go into the loop or into the function call. You will see how the deep copying works in part 2. Okay. So what does AND contain after this function? It contains, oh, for range -1 till 6. Oh, you're creating a copy that has a bigger boundary. Okay, so you're creating a kind of empty grid so that you don't have to deal with neighbors falling out of bounds. You just have a grid that is a bit bigger. And then N2 is the actual normal grid size. So you can always use this one if you need to check out of bounds. So you're copying then all of the grid positions into N so that you have a safe grid. And then you're going over the X and Y dimensions and you're keeping a count. And M is the current cell at that position, and you're also assigning it to N2. But didn't you already do that here? Oh no, you did it only for N, which has an extra buffer around it. But M doesn't have it. Maybe M is the next generation. No, N is the next generation. N2 is the next generation. Yeah. And here just extracting the value. And you're saving N2. Okay, so this is where you're actually storing the next generation. I see. And you're counting. You're doing C plus the previous one, and 1 in case that in the grid with the extra margin you find a hash, otherwise you count nothing. And basically you do that in all directions. And then in the end you decide that if you did have a hash, so you are a bug and the count is not exactly 1, then you're going to die and become a dot. And otherwise, if you're a dot and the count is exactly 1 or 2, then you're going to become a bug, a hash, and that's how you calculate the next generation. And now you do it forever until you find 2 of the same generations. But what didn't work for me is I was just keeping a set, and then I was trying to do blah 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 in set. Oh yeah, that didn't work because a set must be hashable. But what you're doing is you're just appending lists of characters to another list, and then you don't have to use hashable values, and it can just work. Although list is not a hashable value apparently. It's a bit strange. So let's say I make a set called S and I want to add to the set a list with 1, 2, and 3. Yeah, I get a problem unhashable type. But if I would have made just a list instead of a set, I would just have added my thingy, like and then use append instead of add. Then I could just do is 1, 2, 3 in my sets, and it would give me true. And actually it would be just as good because we don't have duplicates in this list because we are breaking as soon as we find our duplicate. So for now on I will use sets for positions, but not for checking duplicates. If I have kind of unpredictable data types, then I'll just use lists. And I'll take the performance hit with that. Okay, that was part 1. And bio, you calculated as such. You also did C in... Yeah, that's true. I did also C in list instead of doing a double check. I just did like this. Yeah, I like it. Not a very great advantage to it. All right. Now for the bio calculation, you're counting Z as 1, and that is kind of your power. So you're incrementing your power, you're doubling it every time. And just as a tiny hint, maybe you just prefer the other way of writing, but you can also write it like this. Probably there are even different ways to write it. Probably you can also write it like this or something. Because then you're shifting your bits to the left, which means that you're doubling. Yeah. Oh gee, you already have to go. That's fine. I'll still continue the review and you can watch it online later if you want. So, very Merry Christmas. And see you again. Hold on. No, it's me. Oh, did I just miss that? Oh, Alex, you're leaving. Alright. Okay, see you, Alex. And have a good day. Merry Christmas. And see you on the next stream. And gee, you're still here. Okay. So, all the different ways to double a number. This is one other way to do it. Let me actually double check that if I have it correct. So let's say we have 2 and we're going to double it. That looks like, oh, wait a second, move it 1 to the left. So if we have a number like x and we do like shift it to the left, then x is now 2. And then if we do it again, then x is now 4. Yeah. Alright, so you're shifting to the left every time, and then if you found a hash at that point, then you're going to add the current power to that total and return the total in the end. Alright, pretty straightforward and clean solution, I would say. Then for part 2, it's a little bit more complicated, of course. Let's see if we can run it. So we have day 24 input. Let's activate it. Oh, I do need to break somewhere actually if I want to see what's going on. Let's do that again. So again, you have your map same way as before, and we don't need to go over that all the way. And then you have also, oh, actually it's stopping on every iteration. That's interesting. Now we have an empty grid with only dots, and we have levels, and you're doing level -101 till level 102. I think G's favorite solution is to just create big boundaries where you know that you're gonna be safe. I've seen you do that already with the int code, where to make sure that you don't get memory out of bounds errors, you just adding 5,000 empty memory locations. And so far I think you have not been getting into trouble for that in Advent of Code. So you're just assuming that you're going to have 100 levels at most in every direction. And of course, again, if it wasn't correct, then you can just crash and you'll know and you'll increase it. And you're using copy.deepcopy. Okay, that is what I need. Import copy. So that's another thing I learned today, how to deep copy stuff. And so you're appending this empty grid, a copy of it also, to all of your maps. And then the first one, you're going to do a deep copy of it. But why not the other ones? Today you can calculate that every 2 turns will increase the levels by 1 up and 1 down. So it wasn't actually a kind of trick. Well, it was a trick, but a different trick. So you calculated that actually. That's very clever. For every 2 turns it will increase. And why every 2 turns and not... Why not every 1 turn? Because if you have a cell on the edge... Oh, because the kind of bugs need to travel like 1 step to the other edge to kind of spread around. Is that the reason? Yeah, because you never create bugs when there's a distance of 1 between you. So at most you could expand 1 at a time. Yeah, okay. That's yeah, now I think about it, it makes sense. So you copy, but why do you copy your original map input Oh, okay, but here you seem to be able to just make slices instead of deep copying, but here you are doing a deep copy. Was there any specific reason for that? Because I found that slices don't work for me as well. Okay, after that we have all the maps and we have all the layers, and then we're going to the place where you actually run the program. It's here. So 200 iterations and you're calculating the next gen. So slices work only for lists of one level. Let's see. Ah, yeah. Yeah, so it has lists of characters, right? Yeah. But, So you can still make a slice of the list, but then you're maybe still copying the rows as a reference. Ah, maybe this is actually an iterator that creates a new list. So it's a new list, so the outer list is not a reference. And then all of the lines in it are also not references anymore. Because the values in it are immutable, they are characters, so they are copied. Right. Yeah, I get it. Okay, so we are now here iterating 200 times and we're calculating what the next generation is going to be. And how does that work? So we have n100. That is probably the new list of maps and 100 times those. You're copying all of them. And it doesn't matter that you copy them, even though you technically need empty maps, or you could have non-values in it. It doesn't matter what value you have in it, as long as it is a fresh copy. Let's go till the next loop. And then you're going over R in the range of -100 till 100. But you didn't go over -101 till positive 102. So how do you know for sure that you're not skipping a range? Maybe it's because you know for sure that the lowest range is -101 and that maybe you're writing to the new range instead of updating the range where you're currently iterating. Let's see if that is true. So n100 is all of the new ranges, and here you're doing all kinds of checks, and R is the range you're currently working on. So that means you're actually updating the current range. So doesn't it seem like now that range -101 will never be updated? Or maybe -100 is actually the real outer bound. I think that's what is happening. -100 is the real outer bound, and 102 is the real bound as well. So you're, or not sure if I'm formulating it correctly, but basically these are the real ranges you're interested in, and you're just adding one more on the bottom and on the top to make sure you don't get out of bounds errors. Then you're going to see what tile is up, left, right, and down. And so if you do have one, you're counting 1. And are you using this value even later? Are you using it somewhere? Yes, here you're using it. Okay, I see what you did. So for the layer above you, you're deciding which tile it is on the upper layer. Okay. But you're saying 1 if it is a hash and otherwise 0. So you're directly checking if the layer above you, on where you're neighboring it, has a bug or not. Yeah. T up is the 8 for A, B, C, D, E. Yeah. So on the right here, that is the 8. I see. But for the position below you, you have to do something different. I want to see where you're doing that. That is basically this part. Yeah, so it's kind of a mirror of this one, except that you're going to have to count many more things. So you're counting 5 times, and you're counting the layer below you or above you, depending on how you look at it, the higher layer, and taking the left side, or no, the first line, and then X that is moving, and you're counting it. And similar ways for the other sides. So here you're checking the right side vertically. No, wait, this is the bottom layer, bottom level, so it's U, V, W, X, and Y. And then you're going from the left to the right. Yeah. Indeed. Oh, our center up is U, V, X, Y, Z for 18. And that is because U, V... For 18, you're checking the bottom layer, right? I think our center up is... It looks like it's counting A, B, C, D, E here. Not sure exactly, but since you're checking Y equals 0 and then X is variable, so it looks like you're checking this part. But it doesn't matter. It's I think it works exactly correct. And our center up is indeed the upper part of the center. Yeah. And then I'm assuming that on the right and the left it will work as well. So I'm not gonna repeat that part. And then N. N. Let's see what N is about. Maybe we can run it all the way up till N. N will contain all empties. So those are kind of counts, I suppose. And so you're counting... Ah, I see what you're doing. Yeah, okay, so you're going over all of the positions in the new grid. And then, if you're counting something, if you had exactly a 1... No, wait a second. Oh, you're assigning a 1 if in the maps that you just populated you have a hash in that particular location. Okay, so that is for the case where there's exactly one bug. But what are you gonna do with these R centers? That I'm not sure about yet. So we're going over all of this. And then in the end, we're done with that. And we get a grid. And what does it look like? It still looks like all empty zeros. Maybe that's because I accidentally ran this code. I think I accidentally ran this code as I was trying to evaluate the N. So sorry, I'm going to run it again until that plays. Like here. So N contains... Oh, it still contains nothing. Okay. And yx is the number of layers neighbors this level has for position yx. Ah, yeah. But why are you counting then only 1? So it can never be 2. Right? Yeah, so for now only level is 0 is useful. So that means that I should check if the R is 0 and then break there. Let's run it. And I'll remove that breakpoint. So now we have level 0, and then we can find actually that N contains a whole bunch of numbers. And but what I'm not entirely sure about is that you have your maps with all of the neighbors, and if there's a neighbor you're counting 1 for that. Ah, okay, you're putting a 1 everywhere there is a bug, basically. That's what you're doing. Yeah, okay. But you're copying it into a new position, or in a new map, sort of. And then you're going over all of the Y positions, so you're checking the left. And so you have the Y position, and on -1, that is... let's see. -1. Not neighbors, but bugs. Yes, sorry, I need to comment better. Yeah, well, that's alright. I know the feeling, you know. You've worked on this in the early morning, and then it's done. And I find it sometimes even hard to understand my own code from the same day. And so let me try to figure this out. So t left is 0 at this point, and t right is also 0, and t up. I think these should all be 0, but I'm not sure. Yeah. So in the end, after you're doing this, you basically have a list of all of the... Oh, ZX Kevin XZ, welcome on the stream and thanks for following. If you're not on the leaderboard yet, which I think you're not, then you might want to join. It's kind of the last day still, but you might like to show up tomorrow on the board. So I'll give you the join code, which is this one. And do let me know your Advent of Code name so that I can match you with your Twitch name. And what you're doing afterwards is you now add the border with the numbers found in the upper level. Yeah, you're adding the border with the number found in the upper level. So what does n contain at this point? So you're containing all kinds of zeros and ones. So this will always be 0 of 1. And then here you're going over the outer borders and maybe the inner border. Yeah. So then you've basically stored... but here you're storing n100, which is the new layers. Yeah. So maybe once we go over it, then we can actually see how it works. So we are the center, and that means that the new position is going to be a dot, and we're going to continue. And then for the next case, we're counting 0. Our current position is a dot, and we're storing the dot in the new grid. And then we're counting all of the directions. And if x is 1 and y is 2, then we're adding also the center left count. Ah, now it starts to make sense, yes. And otherwise, we're adding center right and center up and center down. So for those specific 1, 2, 3, 4 cases, you're doing something extra. That is the center of the grid. And the outside cases are a little bit more complicated. And where do you handle the outside cases then? So, okay. Here, if you're saying that we're a hash and we don't have one neighbor, then we're going to die, and otherwise we are going to live. And so where did you count the outer neighbors? That is here, where you count n, but you're counting only 1. And you're counting 1. So here you're counting the numbers on the left, right, and down. Yeah, I think that is the part where you're counting the outer neighbors. Yeah. So the outside stuff part is starting in line 91-ish. Yeah. I see. Okay, I think I understood it for like 85%, which I think is good enough for now. Thank you very much, G, for sharing your code. I learned a bunch of things again. Thank you very much. Copy and reading lines like this, reading the whole input. So if there's anyone else who has some code to share, Bruno maybe, if you're still here. I'm not sure if you have a holiday today and it's already working time, so you might be at work. It looks like you do have a holiday, so happy holidays. And you haven't tried Pastebin yet, but let's have a look. So you have part 1 and part 2. And till when is your holiday? Are you also staying till after New Year, or are you going to work later at the end of this week? Ah, you're importing unit test. Nice. Accidentally overrode your part 1. Ah, yeah. That can be a good strategy sometimes. Directory till New Year. Nice. So that is going to be Bruno. Part 1. First time it happens this year that you're staying, like having a long holiday. Wow. I think I always take at least 1 week holiday around New Year. Or the first time you overwrote your code. I see. Okay. Yeah, it's sometimes a bit difficult to, you know, one person is talking and the other is chatting, and there's a delay in that. So there I go, kind of misunderstanding what people are saying. That also happens a lot. Oh, you like my Santa hat? Well, thank you very much. It is very funny. Sometimes it doesn't work very well with my green screen, but it's okay. And welcome on the stream, FLMDRG. Is there a better way to pronounce your name than that? Flame Dragon, maybe? Maybe you're Flame Dragon. And a big congratulations to me if I figured that out correctly. You don't have an input file, the file is embedded. Okay, that works. I don't have to run it exactly on my input, that doesn't matter much. So this will also be working. And so here are the long lost tests that I was making in the very beginning, but not anymore later. So I hope that my unit tests are going to work, because my PyCharm was doing a bit weird, working a bit weirdly recently. And look at that. So your testing assignment, testing that the silver part of your puzzle is returning this part, and with the data, and that is your real input data, I think. And you have example 0 also, where you're testing with another input and you're testing a certain output. But how did you test it? Did you find this value by hand, or did you just implement it, and then when you found that you think you have a good solution, that you kept it so that in case of refactoring you wouldn't break anything? FLMDRG is short for Flumdingberg, but I'm flame dragging now according to streamers. You're crying, but you do like it. Flumdingberg. I'll try to keep that in mind. Example 0 is in the description. Ah, right. Oh yeah, so you took it from the description and you just wrote it down so that you can verify that your code is working correctly. Yes, I do see it here. Yeah. Okay, so solve silver. How does that work? You have a history where you encode the world, and the world is the string that you input, I think. And encode the world is basically converting. Yeah, you're creating a set of bugs where you're checking if you have a hash, and you're iterating. You're having a single string without lines, so that basically you can kind of pick that character out of the string using this formula. And it's a very standard formula. I think most of you are familiar with it. Basically, the x just goes up all the time. But you're doing +1, +6. Why is that +6? Oh no, it's +6 times j, and j is the height. And because you have new lines at the end of your line, you don't do +5 times j, but +6 times j. So you're skipping the new line there. Yeah, and the weird part is you did not remove the new line. Well, it worked, and then in the end you have normalized your input. It's clean, you have only the bugs. But I see that you are adding also a 0 here, which is fascinating. I don't know what the 0 is for. Maybe it's the count of the neighbors or something. Let's see. So for, where were we? You have a few helper functions. So I need to look where the code is running. I was doing here example 0 with solve silver, and then seeing how it worked. Yeah, he is just flattening the array, but 0 is the level, so that means that you have expanded your part 1 with a 0. Yeah, that's okay, that's fine. I'll assume that you probably didn't have the level at first. So your history consists of the encoded world as you get it as an input, And then, as long as the last history is not in your history except for the last one, then you're going to keep appending the history and iterating. So this is the kind of next gen function of G, but it's called tick. So we're ticking our world forward based on the last item in the history. Cool. That's a very elegant and descriptive way to do it. And tick is from Game of Life, and it's of course a very common way to call iterations when you're doing renderings. For example, in graphical games you also have ticks, or well, we usually have two different kinds when we do graphical games. We have next steps in our physics simulation, that can be called a tick, and we have the next frame, that would be called a frame. So we're interested in the next tick, and to get a new universe you apply the rules of your old universe, and that looks like this. So we have a function that generates a new universe, and it's based on a location. So actually apply rules is a function. It returns a function. And so this is the new universe function. And then we're creating a new set. For every cell, for every cell we check which neighbors might spawn to life, and then we're keeping them in the set if the new universe tells you that they are gonna be alive. So new universe is a function that returns true if that particular position is going to be alive. That's another very different way of solving it. I like it. So here we decide how our universe works, and apply rules looks like this. So this function says, is it going to be alive or not? You're adding to that new universe is a lazy loaded version of the new universe. Why is it lazy loaded? Do you mean that it's a sparse universe in the sense that you're saying it is, you should think of it as if it was an object, but it is actually a function. But you're calling it also, and you're returning in the end cells. So at this point at least, you're still dealing with simple positions. Okay, I see what you mean. Right. So if it looked like this, then I think we have a conceptual agreement that you think of it as a grid and you can just ask a position for it and it will say true or false. But you use parentheses because it is in fact a function. Yeah. That is cool. Okay. And probably if you would have kind of used a class with a overwritten method get, you could actually do it like that. But it's still a little bit different from your actual universe because your actual universe is a set. So you're not really doing like a cell in new universe or something. But this is clean. This is clean. So we first check all the potential living cells and we apply the rules, and that looked like this. Maybe you can overwrite in, yeah. So we check all the neighboring locations, and for part 1 that is probably something simple, yes. And you're doing an absolute of delta x and a delta y, which should equal to 1, otherwise you're not gonna add it. And why is that? You wanna make sure that you're... that's a bit unexpected. Let's see, so you're adding dx and dy, that makes sense, and this was for the next level, that is not relevant for now. And you're going to check... you're doing -1 until 1. Okay, so instead of passing like a list of dx and dy's, you're basically doing a double loop. Congratulations, Valerie, and one more person who just solved. Valukadari. Valukadari might be Flame Dragon. Oh man, I remember Flame Dragon, but I don't remember the other name, your real name. It was, let me look back. Bloomdingberg. Flumdenberg. Maybe Flumdenberg is Valocudary. So you're doing a double loop, and Valerie, you're done on 22. Good job. Yeah. Double loop, and then you're checking if... Ah, I see. You're checking if your Manhattan distance is 1. I know 1. I know why. Yeah, so I think Bruno, you already explained it. Just like to visualize it. So if you have a grid like this, and you're going over all of the positions, like here, then you actually only want these 4, excluding the middle one. So what you're doing is you're checking the Manhattan distance to the corners and making sure that you don't have a Manhattan distance of 2. So only a Manhattan distance of 1, that is what you're going to check. And it is a different and creative way of getting all of the neighbors. If someone knows a more concise way even to do it, rather than writing them all out, I would be happy to know. I think probably what you can do... Oh, I know. I think I might know. No. I was gonna say doing all the permutations of 0, 1 and -1 or something, but that also doesn't work. So you have something like collections and then collections.permutations. Let's see what that does. No, not permutations, maybe perms? Permutation. Oh, it's from itertools. Okay. Let's have a look. Import itertools as it.permutations. You could probably do x to the power of y not equals 0. Wow. I don't understand it, but I think when I do, I'll be mind blown. So I was thinking about something like 0 and 1, and then you get a generator. So that gives you this. It's not exactly enough. How about all the permutations of 2 with these? That gives you something that is pretty close. Oh, right. Caret is not to the power, but XOR. So you're saying that if they are different, so basically that's the same as x is not y, right? So if x is not y, then you're going to keep it in the list. Yeah. Okay. Well, I'm also curious if this is gonna work. So where one of them is at least 0. So for B, hold on. So the delta for the delta in that one, if 0 in the delta. Yeah, that's 1. It works. It's a bit of a weird way to do it. There's something wrong with this code apparently still. Like this? Yeah. Okay, so that's one way to do it. I'm not sure if it's the best way. It's not the best way for sure. I think writing them all out is even shorter, or are roughly the same. Oh no, this is actually how you write it all out. And definitely people will not be able to understand this very easily. Okay, so extra points to the person who can find the shortest way to get all neighboring positions on a 2D grid. Okay, so here you're checking the neighbors, and also you're checking that you're inside the range, and you're checking that location plus dx is within the range, yes. And sometimes if you're using comprehensions and generators, then you do have to repeat some pieces of your code because you don't have the option of writing inline variables. That is a bit of a downside of using comprehensions. So sometimes writing a loop is actually more concise because you can reuse variables. On the other hand, you might not need those variables. And some people like comprehensions a lot, like Bruno. Yeah. Okay, so now you have all the neighboring locations, which is used in the part here, where you check for potentially living cells. But I was actually here right now. So the new universe for that particular location evaluates. all the neighboring locations, and then it's going to do an intersection with the old universe. Ah. Wow. So you're checking... Hold on a second. You're doing an intersection with the old universe. Okay, I know why. I know. I got it. So, we have a grid here. 3 by 3. And we have a cell here and here. And now we have a grid with all the neighboring positions, which is basically only this part. So that actually contains only these two. And now we're gonna do an intersection of those, so that in the end you get a grid, which is of course a sparse grid with only this X in it, right? And then we're counting it, and then you've basically counted the number of neighbors around you. And then if the number of living neighbors is 1 and the location was in the old universe, then we're going to return true, which means there is a cell. And otherwise, if we have 1 or 2 neighbors and it was dead, then we're going to be alive. Yeah, if you do not read it technically, then it's more easy to understand. Yeah, so if the number of... let's see if we do not read it technically. What does that mean? The number of living neighbors is the number of neighbors that are in our potential neighbor locations and also in the old universe. Like that? Living neighbors are the intersection of living bugs and neighbors. Ah yeah. So from set theory point of view, that also makes sense. That's the kind of definition of it, right? Something to which predicate A and B applies is everything that applies A and B. The intersection of things that apply A and apply B. Okay. So that is going to return true or false, and those are the rules which are only used in the tick function. So we're going to determine our new universe with a cell as an input, and for each cell we're seeing, so for each potentially living cell, we're going to check is it actually living in the new universe, and then we're returning it. Alright, that was the tick, and that is how we generate our histories, and that is the part where we check for the reoccurring history, and then we're returning the biodiversity rating. I won't expect a lot of surprises in here, except I would say that you're decoding your world. You're actually decoding it and then working with the characters rather than working with your positions. And I'm not sure why. Maybe that is a remainder of part 2, and in part 1 you did it in a different way. But so in the end, if you have characters, then you're counting 2 to the power of I, and you're iterating for all the characters in your world. Yeah, okay. Yeah, and so I guess you were trying to be fast also today, but I'm not sure. I guess you woke up after me, so you're probably not gonna be on the global leaderboard today. Yeah. Alright, cool. So that was part 1. And part 2, I guess that is mostly going to be the same, except, cool, thanks for coming on the stream then. Except that the potentially living cells is going to be different, but only the neighboring locations are different. And the neighboring locations actually look the same, except that you're excluding the center position. You woke up just before 6, cool. That's lucky. And so here you're checking that dy and dx is not in the middle, or x and y is not in the middle. Okay, so this function is still the same, but then counting the number of living neighbors. Generate neighboring locations. That must be different then. Yeah, because now we have the dimension from the location that you're putting here in the neighbors list. And so now we're actually checking the delta where we go up and down. I guess we're only going up in this case. And here you have a case where you're going down. So here you're checking if... Actually, you're just generating all the positions. And when you go up, let's see. Wait, but these are just the normal neighboring positions, right? I don't see any special exception handling. So this is the same, only for the same layer. And but I do see a 1 here, which looks to me like you're talking about... but you're not using that. You're not using that. Oh, wait a second. This is not the layer. This is all the different delta and x's, the delta x and y's that you're using. Yes. So the layer that you're adding to your position list is going to be everything with the same layer as the current location. Yes. Okay. So I'm with you there. Now we're going deeper. So that means that what we're going to return, you're going to add inner neighbors. And inner neighbors are those where you subtract 1 from the current layer, where you have... Ooh. Okay, so you have 5 borders. So you're doing 5 times a range loop. And for position 1, 2, you're adding all of these. So from 0, which means x is 0, going all the way down on the left side. And for 2, 1, we're going to go horizontally from the top row and so on. Okay. It's actually quite concise as well. And then you have, so this is your loop, but you have a special case. That is the case. The case is the position that you're looking at. And if your case is exactly position 0 and 1. Oh, wait a second. Oh, if it is the location that we are receiving as our location that we're checking, then we're going to add all those inner neighbors. And why do you only do it for this particular case? Why don't you just add all of them? Oh, I know. Okay, actually you want to add these all the time, but you don't want to add the location itself, right? I'm a bit confused about this part. Wait a second. We have different cases. So the 4 at 163 is looping over the options. I see. Okay, I know. I got it. So yeah, they only are added here, but you're basically checking which of the cases applies to you. So let's say that you are position 1, 2, that is the position you got. Then you need to apply these loops. And otherwise you might need to apply this one. So you're basically applying only one of them. Okay. That's a kind of funny way to do it, because you're trying out all cases and only when it's the right one you're actually gonna save it. Yeah, in that case it is conceptually a bit similar as what I did. And it used to be for loops and you kind of compressed it into something like this. Okay, so this is an improvement over something that you had before. Yeah, that makes sense. And you're asking, Bruno, what we're doing. Maybe I will explain it. Or wait a second, you are already aware of Advent of Code, right? Well, let's see. If I didn't explain Advent of Code, I would do it again. Oh, not at all, you're new here. Okay, so what we're doing is we're doing Advent of Code. It's a programming challenge that lasts for 25 days. It starts on December 1st and ends on December 25th. That means tomorrow is the very last day. And every day we get a puzzle and they get harder and harder. And today we had a puzzle where we get a kind of 2D map where all the hashes are bugs. And we have some specific rules that tell us in the next minute which locations are going to contain bugs and which are not. And then we have a second version of it for part 2 where the cells are actually nested structures where the middle structure is a copy or like a similar structure as the entire structure itself. And so we have cells with neighbors in a very complicated way. So neighbor 8 has like A, B, C, and D as other neighbors. And this, I'm looking now at how Bruno solved this puzzle, and we have already solved it, most of the people on the stream. So we're just doing a little bit of a code review here and learning from each other. So the deeper neighbors are checked, and then you have more at the surface. Yeah, you're welcome. And so if you are at position X, 0, that is all the way on the left, then you're going to add the one that is on the right on the the one on the left on the other layer. Right, that is location 2, which is the layer +1, so 1 layer up. And if you're all the way on the left top corner, then you're going to add 1, 2, and that is here, position 1 on the right and 2 down, that is 12. So 1 is a neighbor of 12 in some way, and that looks like this, that A is a neighbor of 12 because A is equivalent to 1 on the other layer. Yeah. So that's how you add all the neighbors, and then when you've returned the neighbors, probably the rest of your code is going to be exactly the same. Neighbor locations intersected with the old universe, that means you have all the living neighbors, you're counting them, and then the other rules are still the same. And then you're going to run them for 200 iterations. Somewhere in a test, I guess. Yeah. So that is 200 iterations. I think you have probably a function called solve gold or something. Solve gold, yes. And you're encoding the world again and repeating the history and checking the length. I think that is probably not the right function. So it's the last of your tests. So that is test assignment, right? And you're doing multi-tick. Yeah. So multi-tick is doing something else. It just goes over the range that you specify and iterating and getting the new bugs. And then in the end, when you get the bugs, you assert that the length is what you got. Yeah, it got lost a bit, but it's fine. All right, cool. Thank you, Bruno, for sharing, and a very different way to approach it with sets and intersections. Also a nice way and a good addition to our creative toolkit, I think. So thank you for that. Now we've looked at 3 different solutions, and I've streamed for almost 4 hours, so I think that is a good moment to end. Tomorrow is the very last Advent of Code puzzle, not my last stream. You will not get rid of me so soon. Although we do have Christmas, and I am going to the Netherlands to visit my family on 2nd Christmas Day. So that means on the 26th, that is, can I get some dates here on the screen? I don't want my own calendar, but just current calendar. And you're saying that the first example has a lot of suggestions for you from Alex. Ah, yeah. I will need to explain when I'll be streaming after today, exactly. And I am not sure yet, but I do want to kind of keep you hooked. So on Thursday morning, on Thursday afternoon, I'm going to the Netherlands. So that means on 26th of December, I will still be here and I'll be streaming. So for the next 2 days, you can rely on the same streaming times as before. On 27, I'm still going to be in the Netherlands, and I will not have all of my equipment there, unless I would bring it, of course. But I think I'm probably not going to stream on Friday. And then let's say that we hang out again on Saturday 28. So remember that every day from now on, except for Friday. And then on Saturday, I'll also announce to you what I'm going to do in the future. And most likely, I'm going to do 2 streams per week, either in the morning or that means morning of European time. So like sometime around 9 o'clock Belgian time. 9 o'clock Belgian time means 3 a.m. New York time. So that's probably not going to work very well for those from New York. And California time might be around 11 p.m. I'm not sure exactly the time there. But maybe I'll get up early, who knows? Maybe I'll do it at 6 o'clock as I was doing so far. I like it, but I have to see about that. And what we're going to do is, I think for the first few episodes, I'm not entirely sure yet, but what I want to do is reach 100 followers. Right now we are about 65. Thanks also to Flame Dragon. Oh man, bling, bling, bing, ding. Ah man, Floomdingberg. I'm gonna have to take notes. Thanks for following, and when we have 100 followers, we're going to create an AI together, a modular AI that is going to do personal assistance. So for example, you could ask, hey, when is my mom's birthday again? And it would tell you. Or it can tell you, hey, when did I go outside recently? Or it might give you suggestions like, hey, don't you want to call your friend sometime? Or it would just kind of know you and like really know a lot of details. But what it will actually focus on is going to be determined entirely by you, because the AI will be modular and everyone can write their own module that can listen to events that happen on in the person's life, such as chat messages, emails, calendar events, GPS location, and you can just hook into that and write your own little AI module for that. That is the kind of rough idea of it. And on Saturday 28, let me pick that day right now as the date where I will fully announce the AI as I've planned it. And well, we might not have 100 followers. It was my original idea to build an AI with 100 developers. That would be a cool concept, I think. But if we don't have 100 at that point yet, I might still already kickstart it and maybe just show you how I want to set it up. And then once it's ready to go and we can collaborate on it, then I'll release it and we can all program together. Let me know what you think about this idea. Send me a direct message or message me on Twitter. I'm at AnagonLive there. And so for now, we'll continue with Advent of Code. And on day 26, we're also going to do a review of some of the puzzles that we haven't talked about yet. I'm going to review day 22. I haven't solved day 22, and Alex is going to help me with his solution. If you have some cool solutions that you really would like to share, do come on as well, and just send it to me in the chat when we're streaming. Something else I might want to do is get some of you on the stream. I have Discord, so that we can actually invite some of you to talk about their experience with Advent of Code, some tips and tricks for next year, what you've learned, and maybe to do a little run through of one of their solutions. So those are the plans for the next few days. I hope to see you again tomorrow at 6 a.m. or the local time where you are living. Good luck if you haven't solved day 24, and good luck on day 25 tomorrow. Have a very great day and a very Merry Christmas evening. Goodbye.